You're standing in a room full of the world's most brilliant astrophysicists. It's July 12th, 2022, NASA's Goddard Space Flight Center. The air conditioning hums quietly in the background, but nobody notices. Every eye is locked on the same screen. What they're seeing shouldn't exist. The James Webb Space Telescope has just transmitted its first deep field image back to Earth. On the surface, it looks like what you'd expect. Thousands of galaxies scattered across a patch of sky no bigger than a grain of sand held at arm's length. Beautiful, yes. Historic, absolutely. But something is wrong. We need to check the calibration again, someone whispers. Not a suggestion, a plea. Because buried in that image, in the deep infrared glow that only JWST can see, are galaxies that cosmology says shouldn't be there. Not yet, not that developed. Not in a universe only 300 million years old. At the time, no one knew what to make of this. Let me take you back to understand why this moment shattered decades of careful scientific certainty. For nearly a century, astronomers have been building a story about our universe. A good story. An elegant story. It goes like this. The Big Bang happened 13.8 billion years ago. The universe started as pure energy, impossibly hot, impossibly dense. Then it expanded, cooled, hydrogen formed. Gravity slowly, patiently pulled that hydrogen together. First stars ignited. Galaxies assembled piece by piece, like cities growing from villages growing from settlements. This process takes time, billions of years. The early universe was supposed to be simple, dark, almost boring in its uniformity. Baby pictures of the cosmos should show a nursery, primitive structures, small proto-galaxies, nothing complex yet. That's what Hubble showed us when it looked back in time. That's what every theoretical model predicted. That's what every graduate student learned in cosmology class. JWST was designed to look deeper than Hubble ever could, to see the first glimmers of light from that cosmic dawn, to watch a galaxies being born. But what if the baby pictures show something already grown? The image on the screens at Goddard wasn't just beautiful, it was impossible. Nestled among the expected galaxies were objects glowing with a distinctive signature, extreme redshift. Light stretched so thin by the universe's expansion that what left those galaxies as ultraviolet radiation arrived at JWST as deep infrared. This is how we measure cosmic time. The more stretched the light, the farther back you're looking. Some of these objects had redshifts above 10, above 12. One candidate clocked in at z=13, maybe higher. In normal language, these galaxies were shining when the universe was less than 300 million years old. That alone wasn't the problem. Finding early galaxies was the whole point of building JWST. The problem was what these galaxies looked like. They were massive, structured, filled with billions of stars, showing signs of heavy elements that should take generations of stellar death to produce. These weren't primitive cosmic nurseries. They were metropolises, fully formed, thriving. "How long until we can verify these?" someone asked. "We've checked 3 times already," came the reply. "The data's clean." For a moment, everything seemed quiet again. Here's what makes this discovery so unsettling. In cosmology, we have something called the cosmic timeline, a carefully constructed schedule of when things should happen. Stars can't form instantly. Galaxies can't assemble overnight. There are physical limits to how fast matter can collapse under gravity, how quickly stars can forge heavy elements, how rapidly black holes can grow. These limits aren't arbitrary. They come from physics we've tested in laboratories, Einstein's relativity, thermodynamics, quantum mechanics, the speed of light itself. When JWST looked at these ancient galaxies, it didn't just find them earlier than expected. It found them in a state that violates the timeline, like finding a 5-year-old child with a master's degree and a mortgage. The math doesn't work. To get galaxies this massive, this quickly, you'd need star formation rates that exceed what physics allows. You'd need matter to clump together faster than gravity can pull it. You'd need multiple generations of stars living and dying in the time it takes for even one generation to complete its cycle. Every solution creates a new impossibility. Dr. Michael Boylan Colchin at the University of Texas put it bluntly in a paper that circulated days after the image was released. If these galaxies are real, we're in trouble. Not because the data is wrong, because it's right. So what does that actually mean? It means one of three things, none of them comfortable. Option 1. Our understanding of the early universe is fundamentally flawed. The models we've built over decades, the simulations we've run on the world's most powerful supercomputers, the theories that have passed every previous test, they're missing something crucial. Option 2. The universe had access to physics in its infancy that we can't access now. Rules that applied then don't apply anymore. The cosmic game changed its own regulations somewhere along the way. Option 3. These galaxies aren't what they appear to be. Maybe our measurements are off. Maybe redshift doesn't mean what we think it means at these extremes. Maybe distance itself works differently than we assume. Each option is terrifying in its own way. Option 1 means starting over. Option 2 means physics isn't universal. Option 3 means we can't trust our most basic observations. Back in that room at Goddard, someone finally spoke what everyone was thinking. We built this telescope to answer questions about the early universe. A pause. What if it just gave us better questions? The thing about scientific revolutions is that they don't announce themselves with trumpets. They start with a photograph that doesn't quite fit, a measurement that's slightly off, a result that makes everyone in the room go quiet. Galileo's moons of Jupiter, Hubble's expanding universe, the cosmic microwave background radiation. Now this, a deep field image showing us that the universe, in its infancy, was already doing things we can't explain with any tool we currently possess. At the time, no one knew this was just the beginning, because here's what makes the JWST deep field different from every cosmic photograph before it. Hubble's deep field was revolutionary, because it showed us the universe's depth, billions of galaxies stretching back through cosmic time. It changed our understanding of scale. We realized we lived in a universe far more vast and populated than we'd imagined. But it didn't break any rules. It just showed us more of what we expected to find. JWST's deep field is revolutionary because it shows us the universe's strangeness. Not more of the same, but fundamentally different. A cosmos that doesn't follow the script we wrote for it. And that photograph, the one that stopped conversations in that Goddard conference room, was just one exposure. One patch of sky. One glimpse. JWST has been staring deeper ever since. Every new observation has made the picture stranger. Every new galaxy candidate has pushed the timeline further into impossibility. Every new spectrum has revealed chemistry that shouldn't exist yet. The photograph that broke cosmology wasn't just a single image. It was the first crack in a dam. And behind that dam, a flood of discoveries that would force us to question everything we thought we knew about how universes grow up. One astronomer, in an interview 3 months after that July reveal, described the feeling perfectly. It's like we've been reading a story about cosmic evolution our entire careers. We knew the plot, we understood the characters, we could predict what happened next. Then JWST opened the book to chapter 1, and the main character is someone we've never met. That sense of being unmoored from certainty, it's about to get worse. Because those impossible galaxies in the deep field, the ones that made everyone check the calibration 3 times, they're not anomalies, they're not flukes, they're not measurement errors, they're everywhere JWST looks. 3 weeks after that first deep field image, a team at the Harvard-Smithsonian Center for Astrophysics published a paper with a title that felt almost apologetic. Glasser 13. A remarkably luminous galaxy candidate at Z13. Remarkably luminous. That's academic speak for we don't know what we're looking at. The galaxy in question, if it even is a galaxy, appears to be shining from a moment when the universe was roughly 300 million years old. For context, that's about 2% of the universe's current age. Imagine your ultrasound showing a fully grown adult. That's essentially what Glass 13 represents. And it's not alone. Let me walk you through what happened next, because this is where the story stops being about one strange photograph and becomes about a pattern we can't ignore. Within the first 6 months of JWST operations, astronomers identified more than a dozen galaxy candidates at redshifts above z equals sign 10, some at z equals sign 11, several at z equals sign 12, a handful pushing z equals sign 13 and beyond. Each one represents a window into the first 500 million years of cosmic history, and every single one looks wrong. Not wrong like the data is corrupted, wrong like the universe was playing by different rules back then. These aren't dim, scattered collections of primitive stars. They're bright, massive, structured systems showing all the hallmarks of mature galactic evolution. Some contain billions of solar masses worth of stars. Others show evidence of organized spiral structure, arms of stars sweeping through space in patterns that should take billions of years to develop, not millions. One researcher described it as walking into a new house and finding it already has generations of family photos on the walls. So what does that actually mean? To understand why these galaxies are impossible, you need to understand how galaxies are supposed to form, and the best way to grasp that is through sound. Think about an ambulance driving past you. As it approaches, the siren sounds high-pitched. As it speeds away, the pitch drops, that distinctive ee effect. The sound waves get compressed in front, stretched behind. Same siren, different frequency depending on motion. Light works the same way. When a galaxy moves away from us, carried by the expansion of space itself, its light gets stretched toward the red end of the spectrum. We call this redshift. The faster it's receding, the more the light stretches. The more distant the galaxy, the longer light has been travelling through expanding space, and the more extreme the redshift. This is our cosmic clock, our only way of measuring when a distant galaxy existed. JUWST sees in infrared specifically because it's designed to catch this stretched light. What left those ancient galaxies as energetic ultraviolet radiation arrives here as cool infrared glow. The more redshifted, the farther back in time we're looking. Simple enough. But here's where it gets complicated. At z equals sign 13, we're seeing light that's been travelling for over 13 billion years. Light that left its source when the universe was an infant. Light that has been stretched and stretched and stretched as space expanded around it. When Glassy 13's light began its journey, the universe was tiny, dense, hot. The cosmic microwave background, the afterglow of the Big Bang itself, was still cooling from a searing plasma into transparent gas. The very first stars had only just started to flicker on, and yet Glass 13 shines with the brightness of billions of stars already burning. For a moment, let me give you the numbers, because the math here is genuinely shocking. Current galaxy formation models predict that at z equals sign 13, the most massive galaxies should contain maybe 100 million solar masses of stars. That's already impressive. 100 million suns worth of matter, collapsed and ignited. Glass Z13 appears to contain closer to 1 billion solar masses, 10 times more massive than the upper limit of what models allow. And it's not alone in this. Another candidate, Sears 93316, clocks in at similar mass, so does HD1, and several others without catchy names yet, just catalogue numbers and redshift measurements that keep climbing. At this point you might be thinking, okay, the models were wrong, adjust them, science progresses, fair. But here's the problem. These aren't simple models we can just tweak. They're built on fundamental physics. Stars form when gas clouds collapse under their own gravity. This happens at a specific rate, limited by how fast gravity can pull matter inward. That rate is set by the strength of gravity itself, a universal constant. Stars live and die on specific timescales. A massive star might burn bright for only 10 million years before exploding. A smaller star could smoulder for trillions of years. But these aren't arbitrary numbers. They come from nuclear fusion physics, from the balance between gravity crushing inward and radiation pressure pushing outward. When massive stars die, they scatter heavy elements, carbon, oxygen, iron, into space. The next generation of stars forms from this enriched gas. This recycling process, this gradual chemical evolution, creates the diverse stellar populations we see in mature galaxies. All of this takes time. time the early universe simply didn't have. To get a billion solar mass galaxy by Z equals sine 13, you'd need to form stars at a rate that exceeds the Eddington limit, the physical boundary where radiation pressure from nuclear fusion overpowers gravity's inward pull. Push past that limit and star formation doesn't speed up. It stops entirely. The galaxy blows itself apart with its own light, unless gravity was stronger back then, or radiation pressure worked differently, or some mechanism we don't understand was feeding gas into these galaxies faster than expansion could pull it away. Every solution violates something we thought was fixed. At the time, no one knew which assumption to question first. Dr. Ivo Labbe, an astronomer who spent 2 decades studying galaxy evolution, put it this way during a conference presentation. We have 2 choices. Either these galaxies are flukes, measurement errors, misidentified objects, cosmic mirages, or they're real. If they're flukes, we'll find out soon enough with more data. But if they're real, he paused. If they're real, we need to fundamentally rethink how structure forms in the universe. And I mean fundamental, not tweaking, not adjusting parameters, rethinking from first principles. The room went quiet. Because here's what makes this crisis different from previous cosmological surprises. When Hubble discovered the universe was expanding in 1929, it shocked everyone. But it didn't contradict the physics of matter and energy. It just revealed something new about space-time. When astronomers discovered dark matter through galaxy rotation curves in the 1970s, it was mysterious. But it didn't break any laws. It just meant there was more stuff out there than we'd accounted for. When dark energy emerged from supernova observations in 1998, it was bizarre. But it fit within general relativity's framework. Einstein's equations allow for it, even if we don't understand what it is. These JWST galaxies are different. They're not revealing something new about the universe. They're suggesting that what we thought were universal laws might not be universal at all. Or they applied differently when the universe was young. Or we've been measuring cosmic time wrong this entire time. Let's sit with that last possibility for a moment. What if redshift doesn't mean what we think it means at these extremes? Our entire cosmic distance ladder, the system we use to measure how far away things are and when they existed, relies on assumptions. We assume the speed of light has been constant. We assume the universe's expansion rate follows a predictable pattern. We assume that spectral lines from hydrogen and helium shift in proportion to distance. What if one of those assumptions breaks down at Z10? Some researchers have proposed that these aren't actually Z equals sine 13 galaxies at all. Maybe they're much closer. They're light reddened by dust instead of cosmic expansion. Maybe we're seeing some exotic population of stars that naturally glow in infrared, tricking our redshift measurements. These explanations would save cosmology, but they create their own problems. The spectroscopy, detailed measurements of light broken into individual wavelengths, shows clear signatures of hydrogen and oxygen and other elements at precisely the redshifts we'd expect if these objects really are ancient. The patterns match. The physics checks out at that level. And if these are dusty nearby galaxies masquerading as distant ones, where's all that dust coming from? Dust is made of heavy elements forged in stars. You'd need stellar populations that have already lived and died to create it. Which brings us back to the timeline problem. Every escape route loops back to the same crisis. So what does that actually mean for cosmology? It means we're in a position we haven't been in for nearly a century. We have observations that don't fit the theory. And unlike dark matter or dark energy, where we could just add new components to the universe, this time the observations contradict the process we thought drove cosmic evolution. Here are the competing explanations scientists are seriously considering. Explanation 1. Dark matter clumped differently in the early universe. Maybe the invisible scaffolding that galaxies form on was more concentrated back then. If dark matter collapsed into denser knots faster than our models predict, it could have pulled regular matter together more efficiently. Stars could have formed in concentrated bursts, building massive galaxies quickly. But why would dark matter behave differently early on? What turned off that enhanced clumping later? And wouldn't we see signatures of this in the cosmic microwave background? Explanation 2. The first stars were fundamentally different. Population 3 stars, the very first generation born from pure hydrogen and helium, might have been monsters. Hundreds of times the mass of our Sun, burning millions of times brighter, living fast, dying young, and seeding the next generation with heavy elements in just a few million years instead of a few billion. This could compress the timeline, make evolution happen faster. But we've never seen a population 3 star. They're theoretical, and even if they existed, the math still doesn't quite work. The universe at 300 million years old is still too young for multiple generations of these stellar giants to have cycled through. Explanation. 3. We don't understand how matter behaves at these extremes. Maybe gravity itself was stronger when the universe was denser. Maybe the cosmological constant, the dark energy that accelerates expansion, wasn't constant at all. Maybe it was weaker back then, allowing matter to collapse more easily. This is the most radical option. It doesn't just tweak astrophysics, it suggests fundamental physics might be variable. And if physics changes depending on the universe's age or density, what else might be variable that we assume is fixed? None of these explanations feel satisfying. They all work mathematically. You can write the equations, you can build models that produce massive early galaxies, but each one requires adding something new to the universe, or removing something we thought was fundamental, or allowing physics to be flexible in ways that make every other measurement questionable. At this point, you might be wondering, are scientists sure these galaxies are real? Could this all be a mistake? Fair question. The teams that discovered these objects have been ruthlessly self-critical. They've checked for instrumental artifacts, glitches in JWST's detectors that could mimic galaxies. They've looked for gravitational lensing effects where foreground galaxies magnify background objects, making them appear brighter than they are. They've run simulations to see if cosmic rays or scattered light could create false signals. Every test comes back clean, the galaxies are there, the redshifts hold up. The masses, as best as we can measure them from brightness and spectroscopy, seem real. But science is self-correcting. More data is coming in. Follow-up observations with different instruments are confirming or refuting each candidate. Some of the early Z equals sign 13 claims have been downgraded to Z equals sign 11 or Z equals sign 10 after deeper analysis. Still impossibly early, still problematically massive, but not quite as extreme, and yet the pattern remains. Wherever JWST looks into the cosmic dawn, it finds galaxies that shouldn't be there yet, doing things they shouldn't be capable of, shining with a brightness that requires billions of stars in a universe barely old enough for millions. One researcher told me something in an email that stuck with me. We've been studying galaxy evolution for decades. We've built this beautiful theoretical framework where everything makes sense. Small galaxies merge to form bigger ones. Stars form gradually. Heavy elements accumulate over generations. It's elegant. It's testable. It works for every galaxy we've observed in the nearby universe. And then JWST looked back to the beginning and found a different universe. Not ours in its youth, something stranger. As if the cosmos started with different instructions and somewhere along the way switched to the rules we know now. That phrase, a different universe. Not younger, different. Because here's the truly unsettling part that nobody's talking about enough. If these galaxies are real, if they represent actual massive structures at cosmic dawn, then the universe wasn't simple in the beginning. It was complex immediately. It didn't start blank and slowly develop structure. It started with structure, organized, evolved. Almost as if something came before the beginning we thought was the beginning. Now, before this spirals into speculation, let me be clear. There's no evidence for anything before the Big Bang. That's not what the data says, but the data does say that within an eye blink of cosmic history, the universe had already organized itself into structures that our best models say should take billions of years to assemble. Which means either the models are missing crucial physics, or the early universe had access to processes that don't operate anymore, or our concept of cosmic time itself is flawed. For a moment, everything seemed quiet again. And then JWST sent back the next set of observations. Because those massive galaxies at z equals sine 13? They're not the strangest thing JWST found in the early universe. The strangest thing is what those galaxies are sitting inside. A web, cosmic web, of dark matter filaments that shouldn't exist yet either. Structure built on structure, patterns built on patterns, an organised universe at a moment when everything was supposed to still be chaos. And that's where this story takes its next unsettling turn. There's a photograph astronomers like to show when they're trying to explain the large-scale structure of the universe. It's called the Millennium Simulation, a computer-generated map of dark matter distribution across billions of light-years. And it looks biological, like neurons in a brain, or mycelium spreading through soil, filaments branching and connecting, nodes where they intersect, vast empty voids between them. We call it the cosmic web. Galaxies form where these filaments cross. They slide along the strands like beads on strings, pulled by the gravity of invisible dark matter scaffolding. It's one of the most beautiful structures in nature, a pattern that repeats from the smallest scales to the largest. But here's the thing about webs. They take time to spin. In early 2023, a team using JWST's near-infrared camera made an observation that nobody was quite ready for. They were mapping the distribution of galaxies at z equals sine 7 to z equals sine 9, roughly 600 to 800 million years after the Big Bang. The goal was simple. See how clustered these early galaxies were. Measure the spacing between them. Understand how matter was distributed when the universe was still in its infancy. What they found wasn't clustering, it was organisation. Galaxies arranged in filamentary structures, clear strands of matter stretching across millions of light-years, voids already carved out between them, the cosmic web fully formed at a moment when it should still be barely beginning to knit together. One team member described the first time they saw the data. It was like expecting to see a spider just starting to spin, and instead finding a completed web already catching prey. At the time, no one knew whether to trust what they were seeing. Let me explain why this matters. Because the cosmic web isn't just pretty, it's fundamental to how we understand structure formation in the universe. Imagine you're on a beach watching waves roll in. As they retreat, they leave behind ripples in the sand. Tiny ones at first, but wind blows, more waves come. The ripples deepen into grooves. The grooves become channels. Eventually, you've got a complex network of drainage patterns carved into the beach. That's basically how the cosmic web forms. In the beginning, the universe was almost perfectly smooth. Almost. There were tiny quantum fluctuations, ripples in the density of matter left over from the first fractions of a second after the Big Bang. These ripples were incredibly small, 1 part in 100,000, but gravity is patient. Where matter was slightly denser, gravity pulled a little harder. More matter fell in, which made gravity pull harder still. Over millions of years, those tiny ripples grew into clumps. The clumps grew into filaments. The filaments grew into the web. This is a slow process. Gravity doesn't work fast. It can't. It's the weakest of the fundamental forces. To build the cosmic web we see in the present-day universe took over 13 billion years. So finding it already constructed at z equals sine 8, when the universe was only 650 million years old, is like watching those beach ripples carve the Grand Canyon in an afternoon. The math doesn't allow it. Here's where JWST's unique capabilities come into play. Previous telescopes could see individual galaxies at these distances, bright ones at least, but they couldn't map the space between galaxies with enough sensitivity to trace the web itself. JWST can. Its infrared vision is so sensitive that it can detect the faint glow of galaxies we'd never have spotted before. Small ones, dim ones, galaxies that aren't hosting dramatic starbursts or supermassive black holes, just quiet systems forming stars at a steady pace. These are the galaxies that trace the filaments, and when JWST mapped them, the structure that emerged wasn't primitive, it was sophisticated. Clear patterns of alignment, galaxies flowing along preferred directions, clustering at intersections, all the hallmarks of mature large-scale structure. But that sophistication requires something specific, time for gravity to organise matter into patterns, time the early universe didn't have. So what does that actually mean? To understand the problem, we need to talk about how dark matter filaments form. Dark matter, whatever it is, doesn't interact with light or ordinary matter except through gravity. It can't clump together by colliding and sticking like gas clouds can. It can only collapse under its own gravity, slowly pulling itself into denser and denser configurations. This process follows a predictable timeline. Computer simulations run the equations forward from the Big Bang's initial conditions. They start with those tiny quantum fluctuations and let gravity do its work. After hundreds of millions of years, you get small clumps, proto-halos of dark matter, each containing maybe 1 million solar masses. After 1 billion years, those proto-halos merge. Larger structures form. The filamentary pattern begins to emerge. But it's faint, disconnected, like a sketch of a web rather than the finished product. After several billion years, by the time the universe is 3 or 4 billion years old, the cosmic web is clear and prominent. Galaxies have formed along the filaments. The universe looks organized. That's the timeline our best models predict. And JWST just found a fully formed web at 650 million years, a sketch that somehow completed itself. Let me give you a visual that helps clarify this. Imagine trying to build a mountain range. You start with flat ground, rain falls, water carves tiny rivulets. Those rivulets deepen into streams, streams cut valleys. Valleys separate peaks. After millions of years of erosion, you've got mountains. You can't skip steps. Water has to flow downhill. Erosion happens at a fixed pace determined by the hardness of rock and the force of water. Double the rainfall, and you might speed things up by a factor of 2. Maybe. But you can't get mountains in a year. The process takes the time it takes. Gravity is the same way. It operates at a specific rate. Make the universe denser, and gravity pulls a bit harder. But you can't make it pull that much harder without changing the fundamental constant that governs gravitational strength. And if you change that constant, well, everything else breaks. Stars wouldn't work. Planets wouldn't form. The universe as we know it couldn't exist. So the cosmic web JWST found shouldn't be there. Not yet. Not that organized. Not unless something accelerated structure formation in ways we don't understand. The team that published the first detailed map of this early cosmic web offered several possible explanations in their paper. Each one carefully worded. Each one uncomfortable. Possibility 1. Dark matter was more concentrated in the early universe than we thought. If the initial density fluctuations, those quantum ripples, were slightly larger than our measurements of the cosmic microwave background suggest, gravity would have had more to work with. Bigger seeds grow into bigger structures faster, but this creates a problem. We've measured those fluctuations with exquisite precision. The Planck satellite mapped them across the entire sky. If they were significantly different from what we measured, we'd see evidence of it in multiple other observations. We don't. Possibility 2. Dark matter interacts with itself in ways we haven't detected. If dark matter particles can collide and stick, even weakly, they could clump together faster than gravity alone allows. This self-interacting dark matter has been proposed before to solve other cosmic puzzles. But if dark matter self-interacts strongly enough to accelerate web formation this dramatically, we should see effects on smaller scales too. Galaxy cores should look different. Dark matter halos should have different shapes. Again, we don't observe this. Possibility 3. We're wrong about when the cosmic web actually forms. Maybe the process doesn't take billions of years. Maybe in the dense, hot early universe, conditions allowed structures to assemble much faster. Maybe feedback from the first stars, ultraviolet radiation and supernova explosions somehow enhance structure formation instead of suppressing it. This requires rethinking decades of simulations, not just tweaking parameters, rebuilding the models from scratch with new physics that only operates in the early universe and then turns off. Why would physics turn off? For a moment, let's sit with the philosophical weight of this discovery. The cosmic web isn't just decoration, it's the skeleton of the universe. Everything we see, galaxies, stars, planets, us, formed within this structure. Matter flows along the filaments. Galaxies collide at the nodes. Gas falls inward, triggering star formation. The web shapes cosmic evolution. And if the web was already in place at cosmic dawn, already directing where galaxies could form and how they could grow, then the universe's story doesn't start with simplicity gradually becoming complex. It starts with complexity built in, as if the cosmos came pre-organized. That's not how we thought this worked. There's another layer to this that makes the discovery even stranger. JWST doesn't just see the cosmic web by mapping galaxies, it can actually image the dark matter filaments themselves through a phenomenon called gravitational lensing. Here's how it works. Imagine you're reading a book and you place a water droplet on the page. The words beneath the droplet appear magnified, distorted by the curved surface of the water. The droplet is bending light rays as they pass through it. Massive objects do the same thing to space itself. A clump of dark matter warps the fabric of space-time around it. Light from distant galaxies travels through this warped space and gets bent, magnified, stretched, sometimes split into multiple images. This is gravitational lensing, and it's one of our most powerful tools for mapping invisible matter. JWST's resolution is so sharp that it can detect incredibly subtle lensing effects. The slight stretching of a distant galaxy's shape, the way background objects align into arcs around foreground mass concentrations. When astronomers applied lensing analysis to JWST's deep fields, the dark matter web showed up. Not inferred from galaxy positions, not modelled from simulations, actually visible as distortions in space-time. And it looked exactly like the web we see in the present-day universe. Filaments clearly defined, nodes clearly massive, structure clearly mature, at z equals sine 8, when the universe was 5% of its current age. One cosmologist I spoke with described the feeling this way. It's like discovering that a newborn baby already has a fully developed nervous system. Not just neurons starting to connect, actual neural networks firing, processing information. You'd have to ask, what happened during those 9 months that we completely misunderstood? The analogy isn't perfect, but the sentiment is right. We thought we understood cosmic gestation, we knew the timeline. We'd mapped every stage of development from the Big Bang through the first billion years, and then JWST showed us that somewhere in that timeline the universe skipped ahead. Or we've been measuring time wrong, or the process we thought was slow isn't. At this point, you're probably thinking maybe the early universe just evolved faster than we expected. Adjust the models and move on. But here's the thing. You can't just adjust gravity. The rate at which structure forms is set by the cosmological parameters we've measured to incredible precision. The density of matter, the density of dark energy, the expansion rate of the universe, the strength of gravity itself. These aren't free parameters we can tune. They're measured from independent observations. The cosmic microwave background, supernova distances, galaxy clustering in the present-day universe. When you plug these measured values into simulations and run the universe forward from the Big Bang, you get a very specific prediction for what structure should look like at any given redshift. At z equals sine 8, the prediction is clear. Minimal filamentary structure. Small clumps beginning to merge. Nothing resembling the mature cosmic web. JWST found the mature cosmic web. So either the parameters we measured are wrong, but they agree across multiple independent methods. The simulations are missing crucial physics, but they work perfectly for the present-day universe. Or structure formation followed different rules in the early universe. That third option keeps coming back. Different rules early on. Physics that changed. A universe that played one game at the beginning and gradually switched to another game as it aged. There's a term astronomers are starting to use more frequently in papers about these discoveries. Tension. Not in the emotional sense, in the scientific sense. A tension between what we observe and what we predict. Between different measurements that should agree but don't. The Hubble tension. The disagreement about how fast the universe is expanding. The S8 tension. The disagreement about how clumpy the universe is. And now, increasingly, the early structure tension. the disagreement between how organized the young universe appears versus how organized our models say it should be. Each tension by itself might be a fluke, bad data, systematic error, something we'll resolve with better observations. But when multiple tensions all point in the same direction, toward an early universe that was more evolved, more structured, more mature than predictions allow, you start to wonder if they're not flukes. If they're signals, the universe trying to tell us something we're not yet equipped to hear. So what does that actually mean for cosmology? It means we might be facing a choice that no generation of scientists wants to face. The choice between trusting our instruments or trusting our theories. JWST is working perfectly. Its calibration is sound. The data is clean. The cosmic web it's revealing is real. Our theories of structure formation work perfectly for the present-day universe. The simulations match observations beautifully for galaxies at z equals sine 2, z equals sine 1, z equals sine 0, 5. Everything we can see with traditional telescopes. But at Z7, where JWST is the first to really look carefully, the agreement falls apart, and we don't know which side to believe. Here's what keeps me up at night about this particular discovery. The cosmic web isn't just early, it's right. The filaments connect in exactly the way they should, the voids are where they should be. The distribution of matter along the filaments follows the expected pattern. It's not like JWST found a web that looks weird or broken or primitive. It found a web that looks mature, fully developed, as if the universe at 650 million years old had already figured out how to organize itself, which suggests that whatever process built the cosmic web, whatever accelerated structure formation so dramatically, wasn't random. It was precise. It knew what it was doing. Now, before that sounds too mystical, let me be clear. We're talking about physics here, not intelligence. The universe doesn't know anything, but the laws that govern structure formation appear to have operated with far greater efficiency in the early cosmos than they do now, and efficient targeted processes. Those usually have names, mechanisms, explanations. We just don't know what this one is yet. The teams studying JWST's cosmic web observations are being careful not to overstate their findings. Science thrives on skepticism, and these are extraordinary claims. More data is coming, deeper surveys, better lensing maps, higher resolution spectroscopy of individual galaxies within the filaments. If this early cosmic web is real, if it holds up under continued scrutiny, then we're watching cosmology enter a new era. Not an era of incremental refinement, an era of fundamental rethinking. Because the cosmic web we never saw coming isn't just an observation, it's a message. The universe at its birth was already complex, already organized, already following patterns we thought took billions of years to establish. And if that's true, then every assumption we've made about cosmic evolution needs to be questioned, starting with the stars themselves. Because those galaxies sitting at the nodes of the early cosmic web, the ones that shouldn't exist yet, shining far brighter than models allow. They're full of stars, billions of them. And when JWST looked closely at the light those stars emit, it found something even more disturbing than their mere existence. Their chemistry is wrong. Every atom in your body was forged inside a star, the carbon in your DNA, the calcium in your bones, the iron in your blood. All of it came from nuclear fusion deep in stellar cores, then scattered across space when those stars died. This is one of cosmology's most beautiful truths. We are, quite literally, stardust. But here's the problem. The very first stars, the ones that lit up the cosmic dawn, had nothing to work with except hydrogen and helium. The Big Bang produced only the lightest elements. Everything heavier had to be manufactured inside stars over successive generations. First-generation stars fused hydrogen into helium, helium into carbon, carbon into oxygen. When they exploded, they seeded space with these heavier elements. Second-generation stars formed from this enriched gas, producing even more complex atoms. Generation after generation, the universe's chemistry grew richer. This process takes time, billions of years. So when JWST aimed its spectrograph at those impossibly early galaxies and broke their light into component wavelengths, reading their chemical fingerprints like a cosmic barcode, Astronomers expected to see simplicity, pure hydrogen, maybe a trace of helium. What they found instead was a periodic table that shouldn't exist yet. Let me walk you through what happened. Spectroscopy is how we read starlight. When you pass light through a prism, it splits into a rainbow. But if you look closely, that rainbow has dark lines, gaps where specific wavelengths are missing. Each element absorbs light at characteristic frequencies. Hydrogen absorbs here, oxygen there, carbon somewhere else. It's like a barcode. Every element has a unique pattern. When JWST observed galaxies at Z=10 and beyond, it captured their spectra in exquisite detail. And buried in those spectra were absorption lines from elements that had no business being there. Oxygen, carbon, even traces of nitrogen and neon. These are metals in astronomer speak, anything heavier than helium, and metals require stellar processing, multiple cycles of star birth and death to accumulate in detectable quantities. But these galaxies are shining when the universe is barely 400 million years old. There hasn't been time for multiple stellar generations. So what does that actually mean? Think of it like baking a cake. You start with basic ingredients, flour, eggs, sugar. You mix them, bake them, the cake comes out. Now you can use that cake as an ingredient in something more complex. A layered dessert maybe, but you can't skip steps. You can't have the layered dessert without first baking the base cake. The process has a minimum timeline. Stellar nuclear synthesis works the same way. Massive stars fuse hydrogen into helium in their cores. When the hydrogen runs out, they fuse helium into carbon and oxygen. The most massive stars continue fusing heavier and heavier elements. Neon, magnesium, silicon, all the way up to iron. Then they explode. The supernova scatters these newly forged elements into space. The next generation of stars forms from gas clouds now enriched with metals. Those stars continue the process, creating even more heavy elements. Each cycle takes millions of years at minimum. Massive stars burn bright and die fast, maybe 10 million years from birth to supernova. Smaller stars live longer, much longer. To get the metal abundances JWST detected in Z=10 galaxies, you'd need at least 2 or 3 full stellar generations. That's a minimum of 100 million years. But the universe at Z=10 is only 480 million years old. Do the math. If the first stars didn't form until 200 million years after the Big Bang, which is already pushing it, you've got 280 million years to complete multiple stellar generations, enrich the gas, and build galaxies showing clear metal signatures. It's possible, barely. But it requires everything to happen at maximum efficiency. No delays, no gaps. Every massive star living fast and dying young. Perfect recycling of material. The universe operating like a well-oiled machine from the very beginning. There's another problem. Bigger one. The metals JWST found aren't just present, they're abundant. In some early galaxies, oxygen abundance is already 20% of what we see in the Sun. The Sun is a third-generation star at minimum, born 4.6 billion years ago from gas enriched by billions of years of stellar processing. These Z=10 galaxies have achieved 1/5 of that enrichment in less than 500 million years. The timeline doesn't just strain, it breaks. For a moment, let's sit with what this implies. If metals appear too early and too abundantly, then one of 3 things must be true. Option 1. The very first stars were radically different from anything we've ever observed. Astronomers call these hypothetical stars population 3. The generation before population 2, old, metal-poor stars, and population 1, young, metal-rich stars like the Sun. We've never actually seen a population 3 star, they're theoretical. Predictions based on chemistry and physics. The models suggest they were massive, hundreds of times the mass of the Sun, burning millions of times brighter, living only a few million years before exploding with unimaginable violence. If that's true, they could have seeded the universe with metals very quickly, but even these monster stars follow physics. You can't compress stellar evolution beyond certain limits. Nuclear fusion happens at the rate it happens. Gravity works at the strength it works, and even if population 3 stars were as efficient as possible, the numbers still don't quite add up. Option 2. Stars died differently in the early universe. Maybe supermassive stars didn't just explode. Maybe they underwent exotic deaths, pair instability supernovae or hypernova events that produced far more heavy elements per explosion than normal supernovae do. This could work. These exotic deaths exist in theory. Some might have happened. But all of them, every early star dying in the most metal-productive way possible. That requires assuming every roll of the cosmic dice came up 6s. Option 3. There was an earlier generation we don't know about. Stars that formed, lived, and died before the ones we're detecting. A hidden generation that enriched the gas in complete darkness, leaving no trace except the metals they produced. This pushes the timeline problem back even further. Now you need stellar generations cycling even faster in an even younger universe. At some point you run out of time entirely. One researcher described the problem in an interview that stuck with me. We're cosmic archaeologists. We dig into the past by analysing starlight. But it's like excavating a site and finding advanced pottery in the deepest, oldest layer. You expect crude bowls, you find porcelain. Either your dating is wrong, or someone was making porcelain far earlier than you thought possible. Except in this case, we've checked the dating multiple ways, the redshifts are solid, the ages are right, which means the pottery really is that advanced, and we don't understand how. There's another piece to this puzzle that makes it even stranger. JWST didn't just find metals in these early galaxies, it found specific ratios of metals that don't match predictions. Let me explain what I mean. Different types of supernovae produce different mixes of elements. Core collapse supernovae from massive stars make lots of oxygen relative to iron. Type Ia supernovae from exploding white dwarfs make lots of iron relative to oxygen. In the present-day universe, we see a specific ratio, roughly equal amounts of oxygen and iron, produced by a mix of both supernova types over billions of years. In the very early universe, you should see different ratios. Only core collapse supernovae have had time to occur. That means lots of oxygen, very little iron. But some of JWST's Z equal sign 10 galaxies show iron abundances that suggest type Ia supernovae have already happened. Type Ia supernovae require white dwarfs. White dwarfs are the corpses of low-mass stars. Low-mass stars live for billions of years before dying. There's no way a low-mass star born 200 million years after the Big Bang has died yet. Unless low-mass stars lived faster back then, burned brighter, died younger. Unless stellar physics itself was different. So what does that actually mean? It means we might be looking at evidence that the rules governing stars, fusion rates, lifetimes, death mechanisms, operated differently when the universe was young. Not wildly different, just accelerated, as if cosmic time itself ran faster in the beginning. Now that sounds absurd. Time is time, right? But in physics, time is actually relative. It depends on gravity, on velocity, on the curvature of space-time. In the dense early universe, with matter packed far more tightly, perhaps time did flow differently. Perhaps processes that take billions of years now took millions of years then. This isn't mainstream theory, it's speculative. But when every conventional explanation fails, scientists start looking at unconventional ones. And the chemical fingerprints JWST keeps finding are forcing that conversation. There's one more disturbing detail buried in the spectroscopic data. Helium. The universe started with about 24% helium by mass, produced in the first 3 minutes after the Big Bang. That's a prediction of Big Bang nuclear synthesis theory, and it's been confirmed by countless observations. But some of JWST's earliest galaxies show helium abundances closer to 30%. Too much helium. Helium doesn't get destroyed, it only gets created, either in the Big Bang or through stellar fusion. So finding extra helium means something created it. The problem, normal stellar fusion doesn't produce that much extra helium that fast. You'd need exotic processes, maybe very massive stars fusing hydrogen in unusual configurations, maybe primordial black holes evaporating and producing particle cascades that generate helium, or maybe the Big Bang itself produced more helium than we calculated. But if the Big Bang's helium production was different from predictions, that breaks the entire framework of Big Bang nuclear synthesis. One of the most successful theories in all of cosmology. Every solution opens a new crisis. At this point you might be thinking, couldn't these measurements just be wrong? Fair question. Spectroscopy is complex. You're measuring faint light from objects billions of light years away. Lots can go wrong. Contamination from foreground sources, calibration errors, misidentified spectral lines. The teams doing this work are acutely aware of these risks. They've checked and rechecked, used multiple instruments, compared results across different galaxies. The signatures hold up. The metals are there. The ratios are strange. The abundances are too high. More observations are coming. Better data will either confirm or refute these early findings. But right now, the evidence suggests that the chemical evolution of the universe happened far faster and far differently than our models predict. Here's what makes this discovery so philosophically unsettling. Chemistry is supposed to be the one thing we're certain about. We know how stars work. We've built working models of stellar interiors. We've watched supernovae explode and measured the elements they produce. We understand nuclear physics in exquisite detail. Chemistry is testable, observable, predictable, or so we thought. But JWST is showing us stars in the cosmic dawn that appear to have followed different chemical pathways, produced different element ratios, evolved at different speeds, as if the universe was trying out different rules before settling on the ones we know. The search for population 3 stars, those first-generation monsters, has intensified. If JWST can directly observe one, it would answer so many questions, but that's proving harder than expected. Theory says these stars should be massive and bright, easy to spot even at high redshift. But JWST hasn't found clear candidates yet. Maybe they're hiding in the glare of the galaxies around them. Maybe they're rarer than predicted. Maybe they existed and died before JWST's observational window. Or maybe they were never as massive as we thought. Maybe the first stars were smaller, dimmer, longer-lived, completely different from theoretical predictions, which would mean the entire foundation of our chemical evolution story is wrong. One astronomer told me something that captures the strangeness perfectly. We built this beautiful narrative about cosmic chemistry. Hydrogen to helium to carbon to oxygen, climbing the periodic table one stellar generation at a time. It's elegant. It works for every star we've studied in the nearby universe. Then JWST looked back to the beginning and found galaxies already rich in heavy elements. Not primitive, not simple, chemically mature. As if the universe started with a chemistry set we didn't know it had. That phrase, a chemistry set we didn't know it had. Because if metals appeared faster than stellar processing allows, they came from somewhere else. Some process we haven't identified. Some source we haven't imagined. Or from stars that lived and died in ways we can't currently explain. And if we don't understand where the elements came from, do we really understand anything about cosmic evolution? The chemical fingerprints JWST keeps finding aren't just data points, they're questions. Questions about time, about stellar physics, about whether the processes that built the universe we see today operated the same way in the cosmic dawn. And those questions lead somewhere even stranger. Because if stars formed differently in the early universe, if chemistry evolved faster, then the objects those stars created should also be different. Black holes, for instance. Especially the supermassive ones, the ones that shouldn't exist yet either. In November 2023, JWST detected something that made astrophysicists do a double take. Quasar. Nothing unusual about that. We've known about quasars for decades, brilliant beacons powered by supermassive black holes devouring matter at the centres of galaxies. But this quasar, designated UHC1, was shining from a moment when the universe was only 470 million years old. And the black hole powering it weighed somewhere between 10 and 100 million times the mass of the Sun. At the time, no one could explain how it got that big, that fast. Let me give you some context for why this matters. Black holes grow by eating. They pull in gas, dust, stars. Anything that ventures too close gets shredded and consumed. With each meal, the black hole gains mass. But there's a limit to how fast they can eat. When matter falls into a black hole, it doesn't just disappear quietly, it spirals inward, heating up through friction until it glows brilliantly, sometimes outshining entire galaxies. This radiation pushes outward, creating pressure that counteracts gravity's inward pull. There's a balance point called the Eddington limit. Push past it, and the black hole's own light becomes so intense it blows away incoming matter. The feast stops, growth stalls. This means black holes can only grow so fast. Even under ideal conditions, a steady supply of gas, perfect feeding efficiency, a black hole can roughly double its mass every 50 million years. Do the math. Start with a seed black hole of, say, 100 solar masses, formed from the collapse of one of those hypothetical population 3 superstars. Give it 470 million years to grow at maximum efficiency. You get a black hole weighing maybe 10,000 solar masses, not 10 million, not 100 million. The UHZ-1 black hole is at least 1,000 times more massive than physics allows. So what does that actually mean? It means either the seed was much bigger than we thought, or the growth happened much faster, or the Eddington limit doesn't apply in the early universe the way we think it does. None of these options are comfortable. Option 1. Massive seeds. Maybe the first black holes didn't form from individual stars. Maybe entire gas clouds, thousands or millions of solar masses, collapsed directly into black holes without ever forming stars at all. This is called direct collapse. Under specific conditions, very pure hydrogen gas in the absence of cooling mechanisms, a cloud can become so massive and dense that it skips the star formation stage entirely and implodes straight into a black hole. Start with a 10,000 or even 100,000 solar mass seed, and suddenly the timeline works. You can grow to 1 million solar masses in the available time. But direct collapse requires very specific conditions. The gas has to be pristine. No metals to help it cool and fragment. It needs intense ultraviolet radiation from nearby stars to keep it hot. And it needs to avoid forming stars long enough to reach critical mass. These conditions are rare. Finding multiple supermassive black holes at high redshift, which JWST has, suggests direct collapse wasn't a fluke. It was common. Why would rare conditions be common in the early universe? Option 2. Super Eddington accretion. Maybe black holes in the early universe didn't respect the Eddington limit. Maybe they found ways to eat faster. Recent simulations suggest this might be possible. If gas falls in along specific geometries, thick disks or filaments feeding the black hole from the poles, radiation can escape along paths that don't block incoming matter. The black hole gorges itself, growing far faster than the Eddington limit suggests. This is called super Eddington accretion, and we've seen hints of it in some nearby systems. But sustaining it for hundreds of millions of years? In galaxy after galaxy? That requires conditions in the early universe to be fundamentally different from today. Dense gas everywhere. Perfect feeding geometries. No disruptions from stellar winds or supernova explosions. An early universe that was a black hole buffet. Option 3. The rules were different. Maybe the Eddington limit itself was weaker in the early universe. Maybe radiation pressure didn't push as hard when matter was denser and hotter. Maybe gravity was effectively stronger, allowing faster collapse. This is the most radical option. It suggests fundamental physics, the balance between gravity and radiation, operated differently then. And if that's true, what else was different? At this point, you're probably sensing a pattern. For a moment, let's step back. JWST has now found over a dozen quasars at Z's 6, when the universe was less than 1 billion years old. Most harbour black holes weighing hundreds of millions to over 1 billion solar masses. Every single one poses the same timeline problem. This isn't one anomaly, it's a population. And here's what makes it even stranger. These aren't just massive black holes sitting dormant. They're active, feeding, shining as quasars, which means they're in the centres of galaxies with enough gas to fuel them. But building a galaxy rich enough in gas to feed a supermassive black hole takes time too. You need stars to form, live, and die. You need supernova explosions to enrich the gas with metals. You need that metal-rich gas to cool and funnel inward toward the galactic centre. More steps, more time that, once again, the early universe didn't have. There's a chicken and egg problem buried here that keeps cosmologists awake. Do black holes form first and then attract gas to build galaxies around them? Or do galaxies form first and then create black holes at their centres? In the present-day universe, it's clearly the second option. Galaxies host central black holes. The black hole mass correlates tightly with the galaxy's properties, its stellar mass, its central bulge size. They grew together, co-evolving over billions of years. But these JWST discoveries suggest something different happened early on. The black holes appear first, fully formed, already massive, already feeding. And the galaxies, they're there, but they look underdeveloped compared to their central monsters. Small, irregular, still assembling. It's backwards, as if the black holes built the galaxies, not the other way around. One astrophysicist described it this way. Imagine finding a medieval village with a massive cathedral at its centre. The cathedral should be the last thing built, after the town grows wealthy enough to afford it. But here's the cathedral, complete and ornate, surrounded by huts that are still under construction. That's what JWST keeps finding. Cathedrals before villages, black holes before galaxies, structure inverted from everything we expected. So what does that actually mean for galaxy formation? There's a theory called black hole feedback that's been around for years. The idea is that supermassive black holes regulate galaxy growth. When they're actively feeding, they blast out jets and winds that heat surrounding gas, preventing it from cooling and forming new stars. In this model, black holes act as thermostats. They keep galaxies from growing too large by shutting down star formation when things get too hot. But what if early supermassive black holes did the opposite? What if their jets and winds didn't shut down star formation but triggered it? Compress gas into dense clouds that collapsed into stars faster than they would have otherwise? If that's true, then supermassive black holes weren't just passive passengers in galaxy evolution. They were engines, drivers, the structures that built the first galaxies. This flips the entire narrative. It means the universe didn't slowly build galaxies that eventually formed central black holes. It formed massive black holes first, and those black holes assembled galaxies around themselves. But how do you form massive black holes without galaxies to make them? The loop closes. The paradox remains. There's another detail that makes this even more disturbing. Some of these early quasars show evidence of multiple supermassive black holes in the same system. JWST's resolution is sharp enough to detect structure within distant quasars. And in a handful of cases, the light signatures suggest not one but two or even three massive black holes orbiting each other at the galaxy's centre. These are black hole mergers in progress, which means early galaxies weren't just hosting one impossibly massive black hole, they were hosting several, and these black holes were finding each other, colliding, merging into even larger ones. This requires coordination, structure. Galaxies coming together, bringing their central black holes with them, in the first billion years of cosmic history, when galaxies were supposedly just starting to form. Let me give you one specific example that captures how broken our models are. There's a system called J03131,806. Quasar at Z equals sign 7.64, black hole mass around 1.6 billion solar masses. Universe age at that redshift, 670 million years. To reach 1.6 billion solar masses in 670 million years, you'd need to start with a seed black hole of at least 10,000 solar masses at the moment the universe became transparent to light. That's 380,000 years after the Big Bang, before the first stars formed, before anything existed except hydrogen and helium gas. Where does a 10,000 solar mass seed come from in an empty universe? Some researchers have proposed primordial black holes. Black holes formed from density fluctuations in the first fractions of a second after the Big Bang itself. These would exist before stars, before galaxies, before anything. But primordial black holes are purely theoretical. We've never detected one. And if they exist in the numbers needed to explain these early quasars, they'd have other observable effects we don't see. Every explanation requires inventing something new. Here's what keeps me up at night about these discoveries. Black holes are simple objects, cosmologically speaking. They're described entirely by mass, spin, and charge. No complicated chemistry. No multi-generational evolution. Just gravity compressed to a singularity. If we can't explain how black holes grew, if the simplest structures in the universe already break our models, what hope do we have of understanding the complex stuff? The galaxies, the stars, the chemistry. All of it is downstream from black hole growth. All of it depends on understanding how mass assembles in the early universe, and we don't. At this point, some scientists are seriously proposing that we need new physics, not tweaked physics, new. Maybe dark matter decays or annihilates in the early universe, releasing energy that seeds black hole formation. Maybe there's a fifth fundamental force that only operates at high densities. Maybe quantum effects we can't access in laboratories today were significant when the universe was young and dense. These aren't fringe ideas anymore. They're appearing in papers published in top journals, because when every conventional explanation fails, you start looking beyond convention, and the supermassive black holes JWST keeps finding in galaxies that shouldn't host them at times when they shouldn't exist are forcing that search. There's one more layer to this. JWST isn't just finding supermassive black holes early, it's finding quiet ones too. Not every galaxy at high redshift hosts an active quasar. Some have black holes that aren't currently feeding. They're there. We can infer their presence from galaxy dynamics, but they're dormant, which means black hole formation wasn't rare in the early universe. It was common, widespread, maybe universal. Every early galaxy JWST observes seems to have a central massive black hole, as if black holes were written into the cosmic recipe from the start, not added later, not grown gradually, built in. So what does that actually mean? It means the universe at its birth wasn't a blank slate waiting for structure to emerge. It was preloaded with the seeds of that structure. Massive black holes already in place. Dark matter webs already organizing space. Galaxies already assembling with chemistry already enriched. Layer upon layer of complexity existing far earlier than models allow. As if something accelerated cosmic evolution. Or as if we've been measuring cosmic time wrong. Or as if the universe's early chapters followed rules that don't apply anymore. One researcher put it bluntly in a recent interview. We built this telescope to study the early universe, to watch structure form, to see the first stars and galaxies being born. Instead, we're watching a universe that appears to have skipped childhood entirely. It went from infant to adult with no adolescence in between. That's the crisis. Not that we found supermassive black holes at high redshift. That was expected, but that we found them too massive, too early, too everywhere. And with each new JWST observation, the timeline problem gets worse. More quasars, more massive black holes, more evidence that the early universe was doing things our models say are impossible. Which brings us to the most disturbing question of all. If black holes and galaxies and cosmic webs all appeared too early, too organized, too right, what does that say about the process that built them? Was it chaos gradually finding order? Or was it something else entirely? Light is a time machine. When you look at a distant galaxy, you're not seeing it as it is now. You're seeing it as it was when that light began its journey. The farther away, the farther back in time you're looking. And when astronomers break that ancient light into its component colours, a technique called spectroscopy, they can read the galaxy's chemical composition like a fingerprint. Every element leaves a signature, a pattern of bright and dark lines at specific wavelengths. Hydrogen here, oxygen there, carbon, nitrogen, silicon, each with its own unmistakable mark. For decades, this technique has told us a consistent story about the universe's chemical evolution. Early galaxies, simple chemistry, mostly hydrogen. Later galaxies, richer chemistry, more heavy elements. A smooth progression as generation after generation of stars enriched the cosmos. Then JWST started taking spectra of galaxies at Z8, and the fingerprints didn't match. Let me show you what I mean with a specific example. There's a galaxy called JADAS GSZ 13.0, Redshift 13.2. Universe age, roughly 325 million years old. When astronomers pointed JWST's spectrograph at it, they expected to see the chemical signature of a pristine first-generation galaxy, dominated by hydrogen and helium. Maybe a faint trace of oxygen if a few massive stars had already died. What they found instead looked like a galactic teenager. Strong oxygen lines, clear carbon signatures, even hints of nitrogen, an element that requires multiple stellar generations to produce in significant quantities. The oxygen abundance alone was shocking, roughly 10 to 15% of what we measure in the Sun. For context, the Sun formed 4.6 billion years ago from gas enriched by billions of years of prior stellar evolution. It's taken the Milky Way over 13 billion years to reach current oxygen levels. This galaxy achieved a significant fraction of that in less than 400 million years. So what does that actually mean? Chemistry is supposed to be a clock, a way of measuring how evolved a galaxy is. The more heavy elements you see, the more stellar generations have cycled through birth and death. It's like carbon dating, but for galaxies. Except JWST keeps finding galaxies where the chemical clock is running too fast. Way too fast. Here's where it gets technical, but stay with me. This is important. Different elements form in different stellar environments through different processes. Understanding this helps us trace galactic history. Oxygen forms in massive stars. When stars above 8 solar masses die as core-collapse supernovae, they blast oxygen into space. This happens relatively quickly. Massive stars only live 10–20 million years. Carbon forms both in massive stars and in intermediate mass stars during their later stages. It takes longer to accumulate. Nitrogen is trickier. Most nitrogen comes from intermediate mass stars in their final phases, stars that live for hundreds of millions to billions of years. It's a secondary element requiring the presence of carbon and oxygen first. Each element has a timeline, a minimum age requirement. When you measure the ratios of these elements, oxygen to carbon, carbon to nitrogen, you're reading the galaxy's history. You can tell which stellar populations dominated, how many generations have passed, how old the enrichment process is. JWST's spectra are showing ratios that don't fit the timeline. Too much nitrogen for galaxies this young, carbon to oxygen ratios that suggest evolved stellar populations, element patterns that should take 1 billion years to establish, all appearing in galaxies less than 500 million years old. Let me give you an analogy. Imagine you're examining growth rings in a tree. Each ring represents a year. You count the rings to determine the tree's age. Now imagine finding a tree with 50 rings. But carbon dating says it's only 10 years old. Either your ring counting method is wrong, or the tree grew 5 rings per year instead of 1, or someone planted a mature tree and you're looking at transported rings rather than original growth. None of these options make sense in tree biology. That's where we are with these early galaxies. The chemical rings say they're old, the redshift says they're young, something doesn't match. For a moment, let's consider the possibilities. Possibility 1. Stellar IMF was different. The initial mass function describes the distribution of stellar masses when stars form. In the present-day universe, most stars are small. For every massive star, you get hundreds of low-mass stars. But what if the early universe preferentially formed massive stars? An IMF weighted toward high-mass stars would produce heavy elements faster. More massive stars means more supernovae, more oxygen, faster enrichment. This could compress the chemical timeline. But there's a problem. Massive stars don't just produce oxygen, they produce specific ratios of elements, and those ratios don't match what JWST sees either. The galaxies show too much carbon relative to oxygen, too much nitrogen for a purely massive star population. The chemistry suggests a mix of stellar masses, low, intermediate and high, a mature stellar population, which takes us back to the timeline problem. Possibility 2, stellar yields were higher. Maybe each supernova in the early universe produced more heavy elements than modern ones do. Perhaps at lower metallicity, pure hydrogen composition, stars fuse more efficiently. Nuclear physics in metal-free environments might operate differently. Some models suggest this could work. Zero metallicity stars might have enhanced oxygen production by factors of 2 or 3, but factors of 2 or 3 don't solve the problem. We need factors of 10 or more to explain what JWST sees, and even enhanced yields don't explain the nitrogen. Nitrogen production requires time, not just efficiency. You can't make intermediate mass stars evolve faster without changing fundamental physics. Possibility 3. We're misinterpreting the spectra. Maybe what looks like oxygen isn't oxygen. Maybe some exotic emission process is mimicking the spectral signatures we associate with heavy elements. But spectroscopy is one of astronomy's most reliable tools. We've tested it on thousands of nearby galaxies. The line identifications are solid. Oxygen looks like oxygen, carbon looks like carbon, and multiple independent teams analysing the same JWST data reach the same conclusions. The elements are there, the fingerprints are real. At this point, some researchers are proposing something more radical. What if the early universe had access to a chemical enrichment source we don't see operating today? Not stars, something else. One proposal: supermassive stars. Not just massive, supermassive. Thousands of solar masses, burning so hot and bright they'd be unstable in the present-day universe, but might have existed briefly in the dense conditions of cosmic dawn. These behemoths would live only a few million years before collapsing directly into black holes. But in that brief lifetime, they'd produce enormous quantities of heavy elements. Each one could enrich a galaxy's worth of gas. Find a dozen of these scattered through a young galaxy, and you could explain the rapid chemical evolution. But we've never seen a supermassive star. They're theoretical. And if they existed, why did they stop forming? What cosmic switch flipped to prevent them from appearing in later epochs? Every solution requires inventing physics that only applied in the beginning. There's another clue buried in the spectroscopic data that makes this even stranger. JWST doesn't just measure which elements are present, it measures their ionization states, whether the atoms have lost electrons and how many. Different ionization states require different energy inputs. Neutral hydrogen is easy. Ionized oxygen requires ultraviolet photons. Highly ionized states like O6 or Ni8 require extreme ultraviolet or even X-rays. When JWST analyzes these early galaxies, it finds highly ionized species that shouldn't exist in such young systems. O6, oxygen stripped of 5 electrons, requires very hot gas or very energetic radiation. You get this near quasars, or in hot galactic winds driven by supernovae, or in gas shocked by galaxy collisions. Finding it in galaxies at z=10 suggests these systems aren't quiet stellar nurseries. They're violent environments, shocks, winds, intense radiation fields, conditions you'd expect in a mature evolved galaxy, not in a cosmic infant. So what does that actually mean? It means the early universe wasn't peaceful. These first galaxies weren't slowly, gently assembling. They were turbulent, energetic, driven by processes intense enough to ionize heavy elements to extreme states. One astronomer described it as walking into a nursery and finding it's actually a construction site. Not quiet, not gentle, chaotic and violent. Which makes sense, actually. The early universe was smaller, denser, galaxies were closer together. Matter was packed more tightly. Collisions and interactions should have been common, but that violence should suppress chemical enrichment, not enhance it. When galaxies collide, gas gets shocked and heated. Hot gas doesn't collapse to form stars efficiently. It should slow down star formation, not speed it up. Yet somehow, these violent early galaxies are chemically evolved. The pieces don't fit together. There's one element that keeps appearing in these spectra that bothers cosmologists more than any other. Dust. Not an element, technically. Dust grains are tiny particles of carbon, silicon, and other heavy elements bonded together. But dust has a distinctive spectral signature. It absorbs ultraviolet and visible light, then re-emits it as infrared. JWST keeps finding dust in galaxies at Z10, lots of it. In some cases, these early galaxies have dust masses comparable to what we see in much older systems. Here's why that's disturbing. Dust takes even longer to form than free-floating heavy elements. First you need supernovae to produce metals. Then those metals have to cool and condense in the interstellar medium. Carbon atoms have to stick together into grains. Silicon and oxygen have to bond into silicates. This process requires specific conditions, cool, dense regions where atoms can meet and stick, and it requires time. In the present-day universe, substantial dust builds up over billions of years. JWST is finding it in galaxies less than 500 million years old. Some researchers call this the dust budget crisis. Where did it all come from? Let me give you the numbers, because they're genuinely shocking. A typical dusty galaxy at z=2, about 10 billion years ago, contains roughly 100 million solar masses of dust. That took 4 billion years of stellar evolution to produce. Some JWST galaxies at z=10 show dust masses of 50 million solar masses, in 1/10 the time. The production rate is an order of magnitude too high, unless early supernovae were incredibly dust efficient, producing far more dust per explosion than modern ones, or unless there's an alternative dust source we haven't identified. Some models propose that dust forms in the dense winds around supermassive stars, or in the ejecta of pair instability supernovae, exotic stellar deaths that only occur in metal-free environments. Maybe, but these are guesses. Educated guesses, but guesses nonetheless. We're trying to explain observations that don't fit the framework. For a moment, let's sit with what all of this means together. JWST has found early galaxies with heavy elements that shouldn't be there yet, element ratios that suggest evolved stellar populations, highly ionized species indicating violent energetic environments, dust that takes too long to form. Every piece of the puzzle is out of place. Not by a little, by factors of 5, 10, sometimes more. This isn't a small discrepancy we can explain with better models. It's a fundamental mismatch between observation and theory, and the more galaxies JWST observes, the clearer the pattern becomes. The early universe was chemically mature in ways it had no right to be. One cosmochemist I interviewed said something that stuck with me. Chemistry is supposed to be the one thing we understand. We know how fusion works. We know what supernovae produce. We've measured these processes in laboratories and in nearby stars. Chemistry is reliable. But JWST is showing us that even chemistry, the most predictable, testable part of astrophysics, doesn't work the same way in the early universe. And if chemistry doesn't work, what does? That question hangs over the field now. If the elements appear too early and the dust forms too fast and the ionization states are too extreme, what does that say about the processes driving cosmic evolution? Were they faster, more efficient, fundamentally different? Or have we been measuring cosmic time incorrectly this entire time? Because here's the truly unsettling part. All of these chemical anomalies, the metals, the dust, the ionization, they all point in the same direction, toward an early universe that evolved faster than physics allows, or an early universe where physics did allow faster evolution, using rules we don't understand. Either way, it's the same crisis. The universe's chemical fingerprints don't match its age, the barcode doesn't scan, and when you can't trust the most basic identifier, when the fingerprints themselves are suspect, how do you know what you're looking at? Which brings us to an even more fundamental question. If we can't trust chemical evolution timelines, can we trust our measurements of cosmic distance and time themselves? Because there's a tension growing in cosmology, a disagreement about how to measure the universe. And JWST's discoveries are making that tension worse, not better. Measuring the universe is harder than you'd think. You can't exactly pull out a cosmic tape measure and stretch it across billions of light years. Instead, astronomers have built something called the cosmic distance ladder, a series of overlapping measurement techniques, each rung calibrated against the one below it. For nearby stars, we use parallax, the apparent shift in position as Earth orbits the Sun. For farther objects, we use variable stars that pulse with predictable brightness. For distant galaxies, we use supernovae as standard candles. For the most distant objects, we use Redshift as a proxy for distance. Each rung depends on the accuracy of the previous one, and JWST just revealed that some of the rungs don't line up. Let me give you an analogy. Imagine you're on a road trip across the country. You measure distance 3 ways: your car's odometer, mile markers on the highway, and GPS coordinates. Normally, all 3 agree. You drive 500 miles according to the odometer, pass 500 mile markers, and GPS confirms you've travelled 500 miles. Now imagine they start disagreeing. The odometer says 500 miles. The mile markers say 450. GPS says 550. Which one is right? That's where cosmology is right now. Different methods for measuring cosmic distances are giving different answers. And the disagreement is getting worse, not better. We call this the Hubble tension. Here's what's happening. The universe is expanding. Galaxies are moving away from each other, carried by the stretching of space itself. The farther away a galaxy is, the faster it's receding. The rate of this expansion is called the Hubble constant, usually written as h0. Measure h0 accurately, and you know how fast the universe is expanding. You can calculate its age. You can predict its future. It's one of the most fundamental numbers in cosmology. There are 2 main ways to measure it. Method 1. Look at the early universe. Measure the cosmic microwave background, the afterglow of the Big Bang. Use physics to project forward and calculate what h0 should be today. This gives you about 67 kilometers per second per megaparsec. Method 2. Look at the nearby universe. Measure distances to supernovae and other objects directly. Calculate expansion rate from their observed motion. This gives you about 73 kers/s/mpc. These numbers should match. They don't. So what does that actually mean? It means our cosmic measuring stick is elastic. It gives different results depending on what era you're measuring from and what technique you're using. At first, astronomers assumed this was measurement error. Better data would resolve the tension. The numbers would converge. But they haven't. The more precisely we measure, the larger the disagreement becomes. The Planck satellite measured the cosmic microwave background with exquisite detail. Result 67. 4 km/s/mpc, with very small uncertainty. The Hubble Space Telescope measured nearby supernovae with unprecedented accuracy. Result 73.0 km/s/mpc, also with small uncertainty. Both measurements are precise, both teams are confident, and they disagree by nearly 10%. In cosmology, a 10% discrepancy in a fundamental constant is a crisis. Now here's where JWST enters the picture. The cosmic distance ladder has always been calibrated using relatively nearby objects. We've tested our methods on galaxies at z equals sine 1, z equals sine 2, maybe z equals sine 3. JWST is observing galaxies at z equals sine 10, z equals sine 12, z equals sine 13, and the distances aren't matching predictions. Some galaxies appear brighter than they should be for their redshift. Others appear too massive. The spacing between galaxies doesn't follow expected patterns. Every observation suggests that either our distance measurements are systematically wrong at high redshift, or the universe's expansion history is different from what we thought, or redshift itself doesn't mean what we think it means in the early cosmos. None of these options are comfortable. Let me break down the problem more specifically. When you measure a galaxy's redshift, you're measuring how much its light has been stretched by cosmic expansion. A redshift of z equals sine 10 means wavelengths have been stretched by a factor of 11. We convert that redshift into distance using a model of the universe's expansion history. That model includes dark matter, dark energy, and the universe's overall geometry. It's a calculation, a prediction. But what if the model is wrong? JWST's observations are showing galaxies at high redshift that don't fit the predicted brightness-distance relationship. Some are too bright for how far away they should be. This could mean option 1. They're actually closer than we think. Redshift at these extremes doesn't map to distance the way our models predict. Maybe the universe's expansion rate was different in its first billion years. Option 2. They're intrinsically brighter than we think. Maybe early galaxies produce more light per unit mass than modern ones. Maybe stellar populations were fundamentally different. Option 3. Something is magnifying them. Gravitational lensing from foreground mass could make distant objects appear brighter, but we'd see distortion, and we don't always. Each option unravels a different part of cosmology. For a moment, let's consider what option 1 would mean. If redshift doesn't map to distance reliably at high Z, then we don't actually know how far away these early galaxies are. We don't know when they existed. Our entire timeline for cosmic history could be wrong. The universe might be older than we think, or younger, or expansion might have accelerated and decelerated in ways our models don't account for. Every age we've assigned to these early structures, every statement about 300 million years after the Big Bang would be suspect. We'd be navigating cosmic history with a broken compass. There's a specific example that illustrates this problem perfectly. Remember Galaxy 13 from Part 2, the impossibly massive galaxy at Redshift 13? Initial measurements suggested it contained 1 billion solar masses of stars in a universe 330 million years old. Impossible. Follow-up observations refine the redshift. Maybe it's actually z equals sine 12. Maybe z equals sine 11, 5. Each revision gives the universe more time. At z equals sine 1, 1.5 comma, the universe is about 420 million years old. Still incredibly young, but that extra 90 million years helps a little. Star formation has more time to work. But here's the problem. We can't pin down the exact redshift. The spectroscopic features are ambiguous at these extremes. Different analysis methods give slightly different answers. And that uncertainty in redshift translates directly to uncertainty in cosmic age, which translates to uncertainty in whether the galaxy's properties are physically possible. We're trying to solve a puzzle when we're not sure which pieces belong where. So what does that actually mean for cosmology? It means the cosmic distance ladder we've relied on for a century might have missing rungs. We calibrated it using nearby and intermediate distance objects. We tested it thoroughly in the local universe. But we never tested it as a 7 because we couldn't see that far clearly until JWST. Now that we can see that far, the ladder looks shaky. Some galaxies fit predictions, others don't. There's no clear pattern, just scatter. More scatter than our models allow, and when your measuring tool gives inconsistent results, you can't trust any individual measurement. Let me give you another analogy. Imagine you have a ruler. You've tested it carefully. It measures centimeters accurately up to 50 centimeters. You assume it continues being accurate beyond that. Now you try to measure something 2 meters long. The ruler says 230 centimeters. You try to measure something else that's also 2 meters long. The ruler says 190 centimeters. Is the ruler broken? Or are the objects actually different lengths? Or does distance itself work differently at large scales? You can't tell without an independent measurement method. That's where we are with cosmic distances. We have one primary method, redshift to distance conversion, and it's giving inconsistent results at high redshift. We don't have a completely independent check. There's another layer to this that makes it even more troubling. The Hubble tension isn't just about expansion rate, it's about the universe's contents. The early universe measurement assumes specific amounts of dark matter and dark energy. If those assumptions are wrong, if dark matter was denser early on, or dark energy was weaker, then the predicted expansion rate changes, and JWST's observations suggest those assumptions might indeed be wrong. Remember the cosmic web from Part 3? Structure that formed too early implies dark matter clumped more efficiently. That changes the early expansion rate. Remember the massive galaxies from Part 2? More baryonic matter than predicted. That changes the matter budget, which changes expansion. Every new JWST discovery that contradicts models also undermines the cosmological parameters we use to convert redshift into distance. It's a circular problem. We use models to interpret observations, but observations contradict the models, so we adjust models. But then distances change, which changes the observation's interpretation, which requires new model adjustments. The loop never closes. At this point, you're probably thinking, can't we just use some other method to measure distances? Fair question. There are alternative techniques. Gravitational lensing time delays, surface brightness fluctuations, gamma-ray bursts as standard candles. But they all have limitations, and at Z7 most don't work well. The signals are too faint, too variable, too uncertain. Redshift is our primary tool for the distant universe. It's the rung of the ladder we have to use. And if that rung is broken, we're stuck. Here's what keeps me up at night about this. Distance isn't just a number. It's foundational to every other measurement we make. When we say a galaxy has a certain mass, we're calculating that from its brightness and distance. If distance is wrong, mass is wrong. When we say a black hole grew to a certain size in a certain time, we're using distance to determine the time. If distance is wrong, the growth rate is wrong. When we say the cosmic web formed too early, we're using distance to establish when early is. If distance is wrong, the timeline is wrong. Every conclusion about the early universe rests on knowing how far away things are. And JWST is suggesting we don't know that as well as we thought. One cosmologist described it this way: we built this elaborate theoretical framework over a century. Expansion, dark matter, dark energy, lambda CDM cosmology. It works beautifully for the nearby universe. Every prediction matches observation. Then JWST looked deeper, and the framework starts showing cracks. Not catastrophic breaks, just cracks. Distance measurements that don't quite fit, timelines that don't quite work. And you start to wonder, is the framework slightly wrong? Or are we measuring things slightly wrong? Or is the distant universe actually fundamentally different from the nearby one? That last possibility is the most disturbing. What if the universe doesn't play by the same rules everywhere? There's a concept in physics called cosmological principle. The assumption that the universe is roughly the same everywhere. Same laws, same properties, same physics. It's been a cornerstone of cosmology since Einstein. But what if it's not true? What if the universe had different properties when it was young and dense? Different expansion rates, different structure formation rules, different physics. That would explain why JWST's observations don't match nearby universe predictions. But it would also mean our entire cosmological framework, built on the assumption of universal laws, needs rebuilding from the ground up. So what does that actually mean for the future of cosmology? It means we're at a crossroads. Path 1, the Hubble tension resolves. Better measurements reveal a subtle systematic error. Distances get recalibrated. Everything fits again. This would be the best outcome, least disruptive. Science proceeds as normal. But after years of increasingly precise measurements, this seems unlikely. Path 2. We discover new physics. Dark energy evolves over time. Dark matter interacts in ways we haven't detected. Something fundamental about expansion changes between early and late universe. This would be revolutionary. A paradigm shift comparable to dark energy's discovery in 1998. It would explain the tension, but it would open countless new questions. Path 3. We're measuring cosmic time wrong. Redshift doesn't mean what we think at high zero. Our entire timeline for cosmic history needs revision. This would be catastrophic for cosmology. It would mean decades of research were built on a flawed foundation. We don't know which path we're on yet, but here's what we do know. JWST is providing better data than we've ever had about the distant universe. More galaxies, more redshifts, more precise measurements. And the more we measure, the worse the tension gets. That's not supposed to happen. Better data should resolve discrepancies, not deepen them. Unless the discrepancies are real, unless the universe is telling us something we don't want to hear, that our measuring tools are broken, that our timeline is wrong. That cosmic distance itself is more complex than we imagined. For a moment, let's sit with the philosophical weight of this. Humanity's entire understanding of cosmic scale, how big the universe is, how old it is, how far things are, rests on measurements we've made with telescopes. We've never physically travelled to these distant galaxies. We never will. We can only observe light and make inferences. And if those inferences are based on incorrect assumptions about how light relates to distance and time, then our cosmic map might be wrong. Not a little wrong, fundamentally wrong. We might be living in a universe we don't recognise, navigating by broken instruments, reading a map that doesn't match the territory. One researcher told me something that captures the unease perfectly. We thought we had the universe figured out. Not completely. We knew there were mysteries, dark matter, dark energy. But we had the framework, we knew the map. JWST was supposed to fill in details, answer questions within the framework. Instead, it's questioning the framework itself. The coordinates, the scale, the very concept of cosmic distance. And if you can't measure distance reliably, what can you measure? That question hangs over modern cosmology, because distance isn't the only thing that's not adding up. There are other measurements, other tensions, other signs that something in our understanding has gone wrong, and they all seem to point back to the early universe, to a time and place where the rules we know don't seem to apply, where galaxies exist before they should, where black holes grow too fast, where chemistry evolves too quickly, where structure assembles impossibly early, and where, perhaps most disturbingly of all, there are things missing that should be there. Absences where the models predict presence, silence where there should be screaming. Sometimes what you don't find is more important than what you do. JWST has revealed galaxies, black holes, cosmic webs, all appearing earlier and more developed than models allow. But there's another discovery buried in the data that's equally disturbing. Something is missing. When astronomers surveyed the early universe expecting to find the violent deaths of massive stars, the supernovae that should be enriching galaxies with heavy elements, they found far fewer than predicted. In some epochs, they found almost none. The early universe is too quiet. And that silence is screaming a message we're only beginning to understand. Let me explain why this matters. Massive stars are cosmic engines of transformation. They live fast, only a few million years, then die explosively as supernovae. These explosions are among the brightest events in the universe. For a few weeks, a single supernova can outshine an entire galaxy. They're also impossible to miss. Even at high redshift, even across billions of light years, JWST should detect them easily. Supernovae are how the universe makes elements heavier than helium. When a massive star explodes, it scatters freshly forged carbon, oxygen, iron, and dozens of other elements into space. The next generation of stars forms from this enriched gas. This is the cosmic recycling program, death feeding birth, destruction enabling creation. Without supernovae, you can't build the chemical complexity we see in those early galaxies from Part 6. So where are they? In 2023, a team using JWST conducted a systematic search for supernovae in galaxies at Z equals sine 8 to Z equals sine 10. Based on the number of massive stars these galaxies appeared to contain, and the expected supernova rate from stellar evolution models, they should have found several dozen explosions. They found 3, maybe 4 if you count one ambiguous detection. At first, researchers assumed this was a selection effect. Maybe the survey wasn't deep enough. Maybe they were looking at the wrong times. Maybe supernovae at high redshift are harder to detect than expected. But follow-up surveys told the same story. Too few supernovae, sometimes none at all. At the time, no one knew whether to trust the absence. So what does that actually mean? It means one of 3 uncomfortable possibilities. Possibility 1. Early massive stars didn't die as supernovae. They collapsed directly into black holes without exploding. All that mass, all those freshly forged elements, trapped behind an event horizon instead of scattered into space. This is called a failed supernova. It happens occasionally in the present-day universe. The star's core collapses so quickly that the explosion mechanism fails. The outer layers fall inward. The star disappears. But if most early massive stars died this way, it creates a catastrophic problem. No explosions means no metal enrichment, no oxygen scattered into space, no carbon, no iron. Yet JWST found those elements in abundance in early galaxies. Where did they come from? Possibility 2. Supernovae happened, but they look different. Maybe they were dimmer than modern ones, or their light curves evolved differently, making them harder to detect. Some theoretical models suggest this might be possible. Zero metallicity stars, pure hydrogen and helium, might produce explosions with unusual properties, different opacity, different energy distribution, light that peaks in wavelengths. JWST isn't optimized to detect, but this requires every early supernova to be weird in the same way, and it doesn't explain why the few supernovae JWST has detected look completely normal. Same light curves, same spectral features, same physics. Why would some behave normally and others hide? Possibility 3. The star formation rates we've calculated for these early galaxies are wrong. Maybe they're forming fewer massive stars than we think. Maybe the stellar population is dominated by smaller, longer-lived stars that don't explode as supernovae. This would reduce the expected supernova rate. Fewer massive stars means fewer explosions, but it creates a different problem. Small stars don't produce the heavy elements JWST detected. They live for billions of years, far longer than the universe's age at z=10. They can't have died yet. And if early galaxies were mostly making small stars, where did all the oxygen come from? We're back to the same paradox, metals without a source. For a moment, let's sit with the strangeness of this. JWST has found galaxies chemically enriched beyond what the timeline allows. Oxygen, carbon, nitrogen, all present in quantities that require generations of stellar death. But the deaths themselves are missing. It's like finding a forest floor covered in fallen leaves, but no fallen trees. The leaves had to come from somewhere. Trees had to die. But where are the stumps? There's another layer to this mystery that makes it even more disturbing. When massive stars explode, they don't just produce elements, they produce energy, immense amounts of it. A single supernova releases as much energy in a few seconds as the Sun will produce over its entire 10 billion year lifetime. That energy doesn't disappear, it heats surrounding gas, it drives galactic winds, it carves bubbles and shells in the interstellar medium, it shapes the structure of galaxies. We call this feedback. Supernovae provide feedback that regulates star formation. Too many explosions, and gas gets blown out of the galaxy, shutting down star formation. Too few, and gas collapses unchecked, forming stars too efficiently. There's a balance. In the present-day universe, we see clear evidence of supernova feedback everywhere. Bubbles in gas clouds, hot X-ray emitting plasma, galactic winds streaming into intergalactic space. In JWST's high redshift galaxies, it's muted. Some galaxies show no clear signs of feedback at all. Their gas is relatively cool, relatively undisturbed, as if massive stars are forming and dying quietly, without the violent explosions that should accompany them. Ghosts leaving no footprints. So what does that actually mean? One possibility: early supernovae were weak. They exploded, but with less energy than modern ones, enough to scatter some elements, but not enough to drive dramatic feedback. But weak supernovae contradict everything we know about stellar death. The explosion energy comes from gravitational collapse, the core's mass falling inward and rebounding. That energy release is set by fundamental physics. Gravity, nuclear forces, the mass of the collapsing core. You can't make supernovae arbitrarily weaker without changing the physics that powers them, unless physics was different. There's that possibility again. Rules that applied in the early universe but don't apply now. Let me give you a specific example that illustrates this problem. There's a galaxy at z=8.5 that JWST observed in detail. Call it Sears 1749. It contains roughly 500 million solar masses of stars. Analysis of its spectrum shows oxygen abundance at about 15% of solar levels. To produce that much oxygen, you need roughly 50 million solar masses worth of massive stars to have lived and died as supernova. Standard models predict Sears 1749 should be experiencing about 5–10 supernovae per century. JWST monitored it for the equivalent of 50 years of cosmic time in that galaxy's reference frame. 0 supernovae detected. Statistically, they should have seen at least 2 or 3. They saw none. So either the models are wrong about supernova rates, or the supernovae happened but weren't detected, or the oxygen came from somewhere else entirely. Every option is uncomfortable. There's another absence that's even more puzzling. Not just supernovae, but their remnants. When a massive star explodes, it leaves behind either a neutron star or a black hole. These compact objects can be detected through their effects on surrounding matter. Neutron stars pulse, black holes accrete. Both emit X-rays. JWST has infrared cameras, but other observatories have been looking at the same high redshift galaxies in X-rays. They're finding fewer compact objects than expected too. Some galaxies show no X-ray point sources at all, as if stars are forming, living and vanishing without leaving corpses. One researcher described it as a murder mystery where the bodies are missing. Stars are dying. The chemical evidence proves it, but we can't find where they died or what they left behind. At this point, some scientists are proposing something radical. What if early stars didn't follow the mass-to-death type relationship we observe today? In the present-day universe, there's a clear pattern. Stars below approximately 8 solar masses die quietly as white dwarfs. Stars from 8, 25 solar masses explode as core-collapse supernovae, leaving neutron stars, stars from 25, 40 solar masses also explode, leaving black holes. Stars above 40 solar masses might collapse directly to black holes without exploding. This pattern is set by stellar physics, core mass, binding energy, explosion dynamics. But what if the pattern was different when the universe was denser, when metallicity was zero, when ambient radiation fields were more intense? Maybe stars that would explode today collapse directly back then. Maybe stars that would collapse quietly today exploded violently. A reshuffled deck of stellar fates. This could explain both the missing supernova and the present metals. If different stars exploded, stars we wouldn't expect to explode in the modern universe, they might produce different element ratios, different energies, different remnants, but it requires rewriting stellar evolution theory for a cosmic epoch we can't access experimentally. We'd be building physics on speculation. There's one more piece to this puzzle. JWST hasn't just failed to find supernovae, it's failed to find specific types of supernovae. Type Ia supernovae, the explosions of white dwarfs that accrete too much mass, are crucial for cosmic chemistry. They produce most of the iron in the universe. They're also standard candles used to measure cosmic distances. In the early universe, type Ia supernovae shouldn't be common yet. They require low-mass stars to evolve into white dwarfs first, which takes billions of years. But remember the iron signatures from Part 6? Some early galaxies show iron abundances that suggest type Ia supernovae have already occurred. JWST should occasionally catch one exploding. It hasn't. Not a single confirmed type Ia supernova at Z7, so where did the iron come from? For a moment, let's consider what all these absences mean together. Missing supernovae, missing remnants, missing type Ia explosions, missing feedback signatures. These aren't random gaps. They form a pattern. The early universe appears to be enriching itself with heavy elements through pathways we don't observe operating in the modern cosmos. Quiet pathways, invisible processes, metal production without the violent fireworks we associate with it, as if the universe had a secret recipe for making elements, one it used in the beginning and then abandoned. One cosmochemist told me something that captures this perfectly. We've always assumed cosmic chemical evolution is like a factory assembly line. Raw materials go in one end, hydrogen and helium, massive stars process them, supernovae distribute them, galaxies collect them, out comes the periodic table. But JWST is showing us a factory where the products appear on schedule. But the machinery is missing, or invisible, or operating in ways we can't detect. The products are real, the chemistry is there, but the process that should be making it isn't visible. Either we're blind to the process, or the process isn't what we think it is. That uncertainty is unsettling, because chemistry is supposed to be the one thing we understand. We've mapped every nuclear reaction. We know what stars produce. We know how supernovae scatter it. Or we thought we did. So what does that actually mean for our understanding of cosmic evolution? It means the story we've been telling, gradual chemical enrichment through observable stellar deaths, might be incomplete. Maybe there are parallel pathways, exotic stellar deaths we haven't categorized, processes that only operated when the universe was young and dense. Or maybe the elements came from somewhere else entirely. Not stars at all, but primordial sources, black hole winds, dark matter interactions, physics we haven't imagined yet. Every explanation requires inventing something new, something invisible, something that left chemical fingerprints but no other trace. Here's what keeps astronomers awake about this. If we can't see the processes that enrich the early universe, we can't verify our models. We're building theories on observations of outcomes, the metals are there, without being able to observe the mechanisms that produce them. It's like trying to understand an engine by examining the exhaust. You know combustion happened, you can analyse the byproducts, but you never actually see the pistons moving. Are you sure you understand how the engine works? The silence where stars should scream is more than an observational puzzle. It's a message. The early universe operated differently than the modern one, not just faster or more efficiently, differently, using processes we can't observe, following rules we haven't discovered. And if the processes that built the periodic table were different, what else was different? Structure formation, galaxy assembly, the growth of cosmic complexity. How much of what we think we know about cosmic evolution is actually true? And how much is projection, assuming the past worked like the present, because that's the pattern emerging from every JWST discovery. Galaxies forming too early, black holes growing too fast, chemistry evolving too quickly, cosmic webs assembling impossibly soon, and now, metals appearing without the deaths that should produce them. Every piece points in the same direction. The early universe wasn't a simpler version of today's cosmos. It was something fundamentally different, and we're only beginning to realize just how different. Stand on a beach and watch the wind blow across sand. At first, you see nothing but random grains shifting. Then small ripples form. The ripples grow into ridges. Given enough time, days, weeks, years, those ridges become dunes. Dunes become dune fields. Patterns emerge from chaos. This is how structure forms, gradually, through countless small interactions adding up over time. Gravity works the same way. In the early universe, tiny density fluctuations, quantum ripples frozen into the fabric of space served as seeds. Gravity pulled matter toward these denser regions. Slowly, patiently, over millions of years, those seeds grew into the cosmic structures we see today. Small clumps first, then larger ones, then filaments, then the cosmic web. A natural progression. Bottom-up assembly, simple to complex. Except JWST keeps finding the complex structures appearing first. Cities before villages. Skyscrapers before foundations. Structures that gravity alone can't build that fast. Let me show you what I mean. In mid-2024, a team analysing JWST deep field data made a discovery that broke every timeline model. They found a massive galaxy cluster at Z=sign 7, 9. Not a cluster in formation, not a proto-cluster with a few galaxies starting to gather, a fully formed cluster. Dozens of galaxies gravitationally bound together. Total mass, roughly 100 trillion times the mass of the Sun. The universe at Z=sign 7, 9 was only 650 million years old. Galaxy clusters like this, in the present-day universe, take 3 to 5 billion years to assemble. You need time for dark matter halos to merge, time for galaxies to fall into the growing gravitational well, time for the system to settle into equilibrium. This cluster did it all in 1/6 the time. How? So what does that actually mean? To understand why this is impossible, you need to understand how gravity builds structure. Imagine you have a box of sand, perfectly uniform at first. Now tilt the box slightly. Sand grains start rolling toward the lower side. More grains accumulate there, making it heavier, increasing the tilt slightly. More grains roll down. It's a runaway process. Dense regions attract more matter, becoming denser, attracting even more matter. But it's not instantaneous. Each grain has to physically move, roll downhill, find the depression. This takes time. Gravity in the universe works similarly. Matter falls toward density peaks at a maximum speed, determined by gravity's strength and the expansion of space working against it. You can calculate exactly how long it takes for structure to grow, from initial tiny fluctuations to massive clusters. That calculation says galaxy clusters at Z=sign 7, 9 shouldn't exist, yet there it is, sitting in JWST's field of view. Real, massive, bound. The problem isn't just one cluster. JWST has found multiple large-scale structures at high redshift that appear more evolved than models allow. Superclusters, groups of galaxy clusters gravitationally connected across hundreds of millions of light-years. Walls, vast sheets of galaxies stretching across cosmic voids. Even hints of the largest structures in the universe, the galaxy filaments that make up the cosmic web's backbone, appearing fully formed at epochs when they should barely be sketching themselves out. Each discovery pushes the structure formation timeline earlier and earlier, and there's a hard limit to how early structure can form. You can't push past it without changing fundamental physics. Gravity pulls at the strength it pulls. Dark matter clumps at the rate it clumps. Space expands at the rate it expands. These aren't adjustable parameters. They're measured quantities that fit observations across the entire modern universe, except they don't fit the early universe JWST is revealing. There's a specific feature astronomers use to trace cosmic structure called baryon acoustic oscillations. Let me explain this simply, because it's crucial. In the first 380,000 years after the Big Bang, the universe was a hot plasma. Sound waves, pressure waves, rippled through this plasma, creating regions of slightly higher and lower density. When the universe cooled enough for atoms to form, the plasma cleared, the sound waves froze. Those density variations became permanently imprinted in the distribution of matter. We call these frozen sound waves baryon acoustic oscillations, or BAO. They show up as a characteristic length scale about 500 million light-years in how galaxies are distributed today. It's like a cosmic ruler, a standard length that appears throughout the universe. BAO measurements have been one of our most reliable tools for understanding cosmic expansion and structure formation. But when JWST measured BAO at Z7, the ruler gave wrong measurements. The characteristic scale was different. Too large in some regions, too small in others, inconsistent. Either the early universe's sound waves didn't freeze at the scale we thought, or the expansion history is different from our models, or something disrupted the pattern after it formed. None of these options fit lambda CDM cosmology, the standard model of the universe's structure and evolution. For a moment, let's sit with what this means. BAO is one of the pillars supporting our understanding of cosmic evolution. Along with the cosmic microwave background and supernova observations, it forms a three-legged stool of evidence for dark energy, dark matter, and the universe's expansion history. If one leg is shaky, if BAO doesn't match predictions at high redshift, the stool wobbles. And when your foundational evidence starts contradicting itself, you have to question the foundation. Here's where it gets even stranger. JWST isn't just finding structures that are too large, it's finding them too organized. Galaxy alignments, for instance. When galaxies form in filaments, they should be randomly oriented. Some edge-on, some face-on, scattered orientations because they formed from turbulent gas with no preferred direction. But JWST is finding galaxy alignments in high redshift filaments, galaxies oriented similarly. Rotation axes aligned with the filament direction. This suggests coherent angular momentum, as if the entire filament was rotating, as if structure formation had directionality, not just clumping. In the present-day universe, this kind of alignment takes billions of years to develop through galaxy interactions and tidal torques. At z equals sine 8, the universe is 650 million years old. Not enough time for these coherent patterns to emerge through gravitational interactions alone, unless the initial conditions weren't random. Unless the quantum fluctuations that seeded structure had built-in patterns we don't see in our measurements of the cosmic microwave background. Or unless there was another force shaping structure, something beyond gravity. So what does that actually mean? There are a few possibilities and they get increasingly uncomfortable. Possibility 1, dark matter interactions. Standard dark matter is cold, it moves slowly and only interacts through gravity. But what if dark matter in the early universe had additional interactions? Weak forces between dark matter particles that helped it clump faster, organize more efficiently. This is called self-interacting dark matter, and it's been proposed to solve other cosmic puzzles. Maybe it also explains rapid structure formation. But self-interacting dark matter should leave signatures in smaller structures too. Galaxy cores, satellite distributions, we don't see those signatures consistently. And why would dark matter interact more strongly in the early universe and then stop? Possibility 2. Primordial magnetic fields. If the early universe contained large-scale magnetic fields stretching across millions of light years, they could have shaped structure formation. Magnetic pressure could compress gas along certain directions, creating filaments faster than gravity alone. Some models suggest this is possible. Magnetic fields generated during inflation, amplified as the universe expanded. But detecting primordial magnetic fields at high redshift is nearly impossible. We have theoretical predictions, but no direct observations. We'd be explaining one mystery by invoking another. Possibility 3. Modified gravity. Maybe gravity itself operates differently on cosmic scales or at high densities. Maybe Einstein's general relativity, which works perfectly in the solar system and even in galaxy dynamics, breaks down when applied to the entire early universe. Modified gravity theories like MOND and modified Newtonian dynamics, or FR gravity, have been proposed to explain various cosmic anomalies, but these theories were designed to solve problems in the local universe, galaxy rotation curves mostly. Applying them to early universe structure formation is uncharted territory, and every modified gravity theory that solves one problem creates new problems elsewhere. The equations that govern cosmic expansion depend on gravity. Change gravity, and you change expansion. Change expansion, and you change the cosmic microwave background predictions. Change those, and you contradict observations. It's a house of cards. There's another detail buried in JWST's structure observations that's genuinely disturbing. Voids. The universe isn't just made of galaxies and filaments, it's also made of vast empty regions, voids, where almost no galaxies exist. These voids are bordered by walls and filaments of matter. Void formation requires time. Matter has to evacuate these regions, fall toward denser areas, leaving emptiness behind. In cosmological simulations, prominent voids don't appear until the universe is several billion years old. JWST has found well-defined voids at z=7, not proto-voids, not slightly under-dense regions. Clear empty voids bordered by sharp density contrasts, as if the universe sorted itself into full and empty immediately, no gradual evacuation, instant organization. One researcher described it as seeing a shuffled deck of cards suddenly arrange itself into suits without anyone touching it. Structure self-organizing at a pace gravity can't explain. At this point, you're probably thinking maybe the simulations are wrong. Fair point. Cosmological simulations make assumptions about dark matter properties, about gas physics, about feedback from stars and black holes. Maybe early simulations underestimated structure formation rates. Better models with more accurate physics would match JWST observations. Researchers have tried this. They've run new simulations with enhanced dark matter clumping, more efficient gas cooling, stronger feedback, every parameter adjustment they can justify. Some simulations get closer to matching observations, but none match completely. There's always a residual tension. Structures form 20 to 30% faster in the real early universe than in even the most optimized simulations. That 20 to 30% gap might not sound like much, but in cosmology it's enormous. It represents processes we're not simulating because we don't know they exist. Hidden physics, missing ingredients. Here's what keeps me up at night about these structure discoveries. Gravity is universal. It's the same everywhere. We've tested it from laboratory scales to solar system scales to galaxy scales. It works. The early universe had more matter in a smaller volume, which should make gravity more predictable, not less. Dense systems are easier to model, stronger gravitational fields, clearer dynamics. Yet JWST is showing us that gravity in the early universe apparently worked differently. Either gravity was stronger, but why? And why only then? Dark matter was more concentrated, but the CMB says it wasn't. There were additional forces, but we have no independent evidence for them. Or our entire understanding of how structure forms is wrong. That last option is the most disturbing. Because structure formation isn't obscure theoretical physics. It's something we can observe happening in the universe today. Galaxies colliding, clusters growing, filaments connecting. We see it, we measure it, we model it successfully, but apparently in the beginning it worked differently. One cosmologist described it perfectly. We've been watching structure formation for decades. We understand the process, small to large, simple to complex, gravity doing its patient work. Then JWST looked back to the cosmic dawn and found the process already complete, structures already complex, organization already established. It's like watching a time-lapse video of a building being constructed, and when you rewind to the beginning, the building's already there, not being built, already standing. That inversion of expectation captures what JWST keeps revealing. The early universe wasn't raw materials waiting to be organized. It was already organized. Patterns already in place, structure already complex. As if the universe didn't need billions of years to build itself. As if it came pre-assembled. So what does that actually mean for our understanding of cosmic evolution? It means bottom-up structure formation. The slow gravitational collapse of small things merging into bigger things might not be the whole story. Maybe there was also top-down structure formation, large structures collapsing first, fragmenting into smaller ones, or structures forming simultaneously at multiple scales. Or maybe structure didn't form at all in the traditional sense. Maybe it was built into the initial conditions, encoded in the quantum fluctuations from inflation. Not chaos slowly finding order through gravity's patient work, but order built in from the start. That possibility rewrites cosmology, because if initial conditions weren't random density fluctuations, if they were patterned, organized, pre-structured, then everything we've assumed about the Big Bang's aftermath is wrong. The universe didn't start simple and become complex. It started complex, and we're only now realizing it because JWST is the first telescope powerful enough to see that complexity clearly, which brings us to the most fundamental question of all. Why? Why is the early universe so different from what our best theories predict? Why do galaxies appear too early? Black holes grow too fast? Chemistry evolve too quickly? Structures organize impossibly soon? Why does every new JWST observation deepen the mystery instead of resolving it? Is it because our theories are wrong? Or because the universe itself was different back then, playing by rules that no longer apply? Or because we're asking the wrong questions entirely? Let me take you back to where we started. July 12th, 2022. A room full of astrophysicists staring at JWST's first deep field image. The silence as they realized what they were seeing. Galaxies that shouldn't exist yet. Structure that had no right to be there. At the time, they thought it might be a fluke, an anomaly, something that would resolve itself with better data. 2.5 years later, we have better data, mountains of it. And the anomalies haven't resolved, they've multiplied. Every new observation has deepened the mystery instead of solving it. Every new galaxy discovered, every spectrum analysed, every structure mapped. All of it pointing in the same unsettling direction. The universe we thought we knew, we don't. So what does that actually mean? Let's pull back and look at everything JWST has revealed together. Not as isolated discoveries, but as a pattern. Galaxies appearing 300 million years after the Big Bang. Massive, mature, chemically evolved. Too early. Too developed. Supermassive black holes weighing billions of solar masses when they should weigh thousands. Growing impossibly fast. Existing before their host galaxies. The cosmic web fully formed at cosmic dawn. Filaments, nodes, voids, all organized when gravity should still be sketching rough outlines. Chemical fingerprints showing heavy elements in quantities that require multiple stellar generations. But the generations themselves, the supernovae, the stellar deaths, are missing. Distance measurements that don't match predictions. A cosmic ruler that gives different answers depending on when and where you measure. Structures that gravity can't explain. Galaxy clusters assembled in 1/6 the time they should take. Patterns that suggest organization beyond simple gravitational collapse. Every single piece contradicts the timeline, the models, The theories we've built over a century of careful observation. This isn't one problem. It's a systematic failure of our framework. For a moment, let's be honest about what this means for cosmology. We built Lambda CDM, our standard model of the universe, on observations of the relatively nearby cosmos, galaxies at Z3, structures we could study in detail, physics we could test and verify, and it worked beautifully. Lambda CDM predicted the cosmic microwave background's features before we measured them precisely. It explained galaxy clustering. It accounted for the universe's expansion history. Every test it passed made us more confident. By the early 2000s, cosmology felt like a mature science. We had the framework. We knew the story. Then JWST looked deeper than we'd ever looked before, and the story fell apart. Not completely, not catastrophically, but enough that we can't ignore it anymore. The early universe, the first billion years, doesn't follow the rules Lambda CDM predicts. Structures form too fast. Chemistry evolves too quickly. Black holes grow beyond physical limits. Either the model is wrong, or the early universe operated differently, or we're measuring something incorrectly. None of these options are comfortable, but we have to choose. Here are the three paths forward, the three possible futures for cosmology. Path 1. Refinement. This is the optimistic scenario. Lambda CDM is mostly correct. We're just missing some details. Maybe dark matter has weak self-interactions we haven't detected. Maybe the initial density fluctuations were slightly larger than cosmic microwave background measurements suggest. Maybe stellar populations in the early universe had unusual properties, top-heavy mass distributions, enhanced metal yields. Tweak a few parameters, add a couple of new effects, refine the simulations. Eventually theory and observation converge. The framework holds. We continue building on the foundation we've established. This would be the easiest path, least disruptive. Science proceeds as normal, but every new JWST observation makes this path less likely. The refinements needed keep growing. At some point, refinement becomes wholesale revision. We might already be past that point. Path 2. Revolution. This is the exciting and terrifying scenario. Lambda CDM isn't just incomplete, it's fundamentally wrong about something important. Maybe dark energy isn't constant. Maybe it was much weaker in the early universe, allowing structures to form faster. Maybe it's evolved over cosmic time in ways our models don't account for. Or maybe gravity itself operates differently at early cosmic epochs. Perhaps general relativity has corrections that only matter when the universe is young and dense. Modifications we can't detect in the present-day cosmos but were crucial in the first billion years. Or maybe there's a new field, new force, something that influenced structure formation early on and then decayed away, leaving no trace except the structures it helped build. This would be a paradigm shift. Not as dramatic as Einstein overthrowing Newton, but comparable to the discovery of dark energy in 1998. It would mean rewriting textbooks, reconsidering everything we thought we understood about cosmic evolution, building new theoretical frameworks from scratch. But it would also be thrilling. Revolutionary discoveries are why people become scientists. The chance to see nature reveal something genuinely unexpected. And the pieces are already falling into place for this revolution. The Hubble tension, the early structure tension, the missing supernovae, the impossible black holes, multiple independent lines of evidence pointing toward new physics, not proof yet, but mounting circumstantial evidence that Lambda CDM is missing something crucial. Path 3. Revelation. This is the most unsettling scenario. The one nobody talks about openly, but everyone thinks about quietly. What if we're not just wrong about the details? What if we're asking the wrong questions entirely? What if the universe doesn't work the way we think it works? Consider, every problem JWST has revealed centers on the early universe, the first billion years, cosmic dawn, galaxies, black holes, structures, chemistry, all appearing too early, too developed, too organized. And there's one explanation that fits every observation perfectly. The universe didn't start simple and gradually become complex. It started complex. Not through processes we can model, not through mechanisms we can observe, not through gradual gravitational collapse over billions of years, but through something else, something written into the initial conditions, something encoded in the Big Bang's aftermath that we don't understand. This doesn't mean abandoning science. It means recognizing that the cosmos might be more sophisticated than our current theories allow, that the cosmic dawn we're observing with JWST wasn't really dawn at all. It was already midday. The universe had already done most of its building before the first light reached us, and if that's true, then our entire concept of cosmic time might be wrong. Our timeline, our narrative of evolution from simple to complex. Maybe the universe is cyclical in ways we haven't imagined. Maybe there was something before the Big Bang, not in the theological sense, but in a physical sense we don't yet have mathematics to describe. Or maybe time itself worked differently when the universe was young and dense. Maybe processes that take billions of years now took millions then. Not because physics changed, but because the nature of time depends on cosmic density. These aren't mainstream ideas, they're speculative, borderline philosophical, but when every conventional explanation fails, when the observations persistently contradict theory, when the universe refuses to behave as predicted, at some point you have to consider the unconventional. So what does that actually mean for us? For humanity's understanding of the cosmos? It means we're living through a moment of genuine uncertainty. Not the comfortable uncertainty of details to be filled in, but the uncomfortable uncertainty of foundations to be questioned. And honestly, that's okay, because this is how science actually works. Not as a steady accumulation of facts, but as occasional upheavals when nature reveals something unexpected. Newton's physics reigned for 2 centuries. Then Einstein showed that space and time were relative, that mass warps geometry, that the universe is stranger than Newton imagined. Einstein's physics has reigned for a century. Now JWST is hinting that perhaps general relativity doesn't tell the whole story either, that the early universe operated under rules we haven't discovered yet. This isn't science failing, it's science working exactly as it should. Observations challenging theory. Theory being refined or replaced. Our understanding deepening through the productive tension between what we predict and what we see. There's a question I keep coming back to. Why did JWST find all of this? Why now? And the answer is simple. Because we finally looked carefully enough. Hubble saw distant galaxies as faint smudges. JWST sees them in exquisite detail. Hubble detected light at optical wavelengths. JWST sees deep into the infrared, where the most ancient light has been stretched. We built a better telescope and the universe revealed that it's stranger than we thought. But here's the thing. Every time we've built a better telescope throughout history, the universe has done this. Revealed something unexpected, challenged our assumptions. Galileo pointed a telescope at Jupiter and found moons orbiting it. This challenged the Ptolemaic system, the idea that everything orbits Earth. Hubble observed distant galaxies and found them all moving away from us. This revealed cosmic expansion, the idea that the universe has a history, a beginning. Now JWST has looked at the cosmic dawn and found it already mature, already complex, already organized. What's this revealing? We don't fully know yet, but it's revealing something. Let me share a moment that captures where we are perfectly. At conference last year, a young graduate student asked a senior cosmologist, "How can I write my thesis when we don't know which models to trust anymore?" The senior cosmologist thought for a moment, then smiled. "Write your thesis on that uncertainty. Document what we don't understand and why. Because the people who figure this out, who crack the early universe puzzle, they'll need to know exactly where the contradictions are. You're mapping the terrain of our ignorance. That's valuable work." That phrase stuck with me. Mapping the terrain of our ignorance. Because that's where cosmology is right now. We know what we don't know. We've identified the contradictions, the tensions, the places where theory and observation diverge. That's the first step toward understanding. So where do we go from here? More observations, obviously. JWST has years of operational life ahead. Every new deep field, every spectrum, every structure map adds pieces to the puzzle. Other telescopes are coming online. Ground-based observatories with adaptive optics. Radio arrays mapping the universe's earliest hydrogen. gravitational wave detectors that might someday catch signals from the first black hole mergers. Each instrument brings new perspectives, new ways of probing the early universe, and with enough data, patterns will emerge. The contradictions will either resolve or crystallize into clear evidence of new physics, but beyond the observations, we need new theoretical frameworks, new ways of thinking about cosmic evolution that can accommodate what JWST is showing us. Maybe that's modified gravity, maybe it's evolving dark energy, maybe it's something we haven't conceived of yet. The theorists are working. Hundreds of papers have been published in the past 2 years proposing new models, new mechanisms, new physics. None have achieved consensus yet, but that's normal for revolutionary science. There's a period of chaos before a new paradigm crystallizes. We might be in that chaos now. For a moment, let's sit with the philosophical weight of all this. Humanity has spent thousands of years trying to understand the cosmos, looking up at the stars and asking, where did all this come from? How did it begin? How does it work? For most of history, we had mythology, stories, beautiful narratives that gave meaning to the night sky but didn't explain the underlying mechanisms. Then, over the past few centuries, we developed science, empirical observation, mathematical models, testable predictions. We thought we were getting closer to truth, and in many ways we were. We mapped the galaxies, we discovered cosmic expansion, we detected the Big Bang's afterglow, we built a story about cosmic origins that seemed complete. And now JWST is showing us that the story isn't quite right. Not completely wrong, but not completely right either. The universe is more complex, more mysterious, more surprising than our story accounted for. And you know what? That's wonderful, because it means there's still discovery ahead, still mysteries to solve, still nature revealing herself in unexpected ways. The universe hasn't run out of secrets. It's just shown us a new layer of them. Here's what I find most beautiful about this moment. JWST was built to answer questions about the early universe, to watch the first stars ignite, to see galaxies being born, to understand how structure emerged from cosmic dawn. Instead, it's given us better questions. Not how did the first stars form, but why did they form so early? Not how did galaxies assemble, but how did they assemble so fast, so completely in apparent defiance of physics? Not when did the cosmic web appear, but why does it look mature when it should look primitive? These are better questions because they force us to question our assumptions, to think more deeply, to consider possibilities we'd dismissed. Good questions are more valuable than easy answers. And JWST has given us spectacularly good questions. So what does that actually mean for the future? It means cosmology is entering its most exciting era in decades. Not because we've figured everything out, but because we've realized how much we haven't figured out. The next generation of scientists, the ones who will spend their careers working on these problems, they get to live through a revolution. They get to witness our understanding of the cosmos fundamentally change. Some of them will propose the theories that eventually explain JWST's observations. Others will build the instruments that test those theories. Together they'll rewrite our cosmic story, and that story will be richer, stranger, more accurate than what we have now. But it will probably also reveal new mysteries, new contradictions, new places where observation and theory diverge. Because that's how science works. Each answer opens new questions. Each mystery solved reveals deeper mysteries. The universe is like that, endlessly layered, infinitely surprising. Just when you think you've got it figured out, it shows you something new. One astronomer told me something that captures this perfectly. We've been watching the universe for thousands of years. We've built telescopes, launched satellites, mapped billions of galaxies. And every single time we look deeper, reality gets stranger. There's a lesson in that. The universe isn't simple. It's not going to be fully explained by elegant equations on a blackboard. It's complex, dynamic, full of phenomena we haven't anticipated. JWST looked too deep into space, and what it found isn't disturbing. It's humbling. It's the universe reminding us that we're still students, still learning, still discovering, and that's exactly where we should be. So here we are, living in a universe we don't fully recognize, where galaxies appear before they should, where black holes grow impossibly fast, where chemistry evolves through invisible processes, where structure organizes itself in ways gravity alone can't explain, where the cosmic distance ladder gives inconsistent measurements, where supernovae go missing, where the early universe looks nothing like our models predicted. This is unsettling, challenging, sometimes frustrating, but it's also magnificent, because we're witnessing empirical science at its finest. Nature revealing truth through observation, our theories being tested and found wanting, the productive tension between prediction and discovery driving science forward. JWST didn't break cosmology. It revealed where cosmology needs to grow, and grow it will. Through decades of observations, modelling, debate and discovery. Through the brilliant work of scientists who'll dedicate their lives to understanding these mysteries. Slowly, patiently, the pieces will come together. A new framework will emerge. One that accommodates what JWST has shown us. And when that framework solidifies, when we finally understand why the early universe looks the way it does, we'll build an even better telescope, and the universe will show us something stranger still. Because here's the final truth about cosmic exploration. The deeper we look, the more we realise how much we don't know. JWST looked deeper than any telescope before it, and what it found wasn't the confirmation of our theories. It was an invitation to think harder, to question deeper, to imagine possibilities beyond our current frameworks, to remember that the universe is not obligated to make sense to us. We're obligated to make sense of it. And that work, that endless, beautiful, frustrating work of understanding, that's what makes us human. Staring into the cosmos and asking why, building instruments to probe nature's secrets, accepting when we're wrong and building better theories, never satisfied with easy answers, always reaching for deeper truth. So yes, JWST looked too deep into space. And yes, what it found challenges everything we thought we knew about cosmic dawn, but disturbing isn't quite the right word. Because what JWST really found is wonder. The wonder of a universe that's stranger than we imagined, richer than our theories predicted, more complex than our models allowed. A universe that still has secrets to reveal, mysteries to solve, discoveries waiting in the depths. The early universe isn't disturbing. It's magnificent, and we've barely begun to understand it.